Hello, test, test. Amazing. All right, welcome to our live studio audience, to anyone joining remotely. This is Anoma Research Day, so if you are not here for Anoma Research Day, you might be in the wrong place. Check your URL bar. To those who are joining us, thank you very much. To the live audience, thank you. What is Anoma Research Day, you might be wondering. So to me, Anoma Research Day is our attempt to give you a snapshot of research in progress. If you imagine Anoma Research as this sort of magic black box, into which flows some talent and a lot of time, and out of which eventually pops fully fledged, idealized perfect Anoma, we are smashing that black box with a hammer and giving you a sort of cross-section peek into its internal workings. So expect works in progress, expect a lot of ideas, expect ideas that may change, and we're looking for, for inputs, for feedback to open up new avenues of collaboration, etc. So what do we have prepared for you today? Today we have 3 tracks. Each track has 2 or 3 presentations, and they will be split by 20-minute or so breaks, so you have a chance to think about it, maybe ask some questions that you didn't think of originally, take a coffee break, etc. The first track is Resource Machine Menagerie, the second track, Distributed Systems Delights, and the third track, Systems Design Selections. We're working with some Swiss chocolate companies to convert these into flavors, but they haven't returned our calls yet. So first track, Resource Machine Menagerie. We will start off with Michael, who you will see just right up next, talking about the EVM protocol adapter, followed by Xiang talking about the Cairo resource machine, and then Kike and Yulia talking about shielded state synchronization. After that, we'll have a little break and start Distributed Systems Delights, which will kick off with Isaac on Store, Order, and Execute, the Anoma node execution system, followed by Anthony on the shard and executor engines, and last but not least, Jamie on a declarative approach to specifying distributed algorithms. Finally, the last track, Systems Design Selections, will start with Jeremy talking about on the System of Anoma, followed by Tobias talking about the Anoma engine system, and I will give the last short closing presentation, which contains a recap and a sneak peek of what might be next. Enjoy our presentations. Please feel free to send us questions and feedback in the chats. We will monitor the chat and responses both on YouTube and on Twitter or X, and we will do our best to surface questions that you put there and ask them directly to the presenters, and you can hear their responses live. We'll also take questions from the live studio audience. Also feel free to send us feedback afterwards, what was useful, what was not useful, what aspects of Anoma Research are you curious about that you might like to see next time, etc. All right, and next will be, in 1 minute, we will start off with Michael.
Thank you so much.
Would you want to introduce him, or you can go right away?
You can go. You can introduce yourself.
Can you adjust the mic slightly lower so you're not breathing in too much? Thank you.
Okay, I'm Michael, and I will today present you the work I've doing for the past 2 months about the EVM protocol adapter and how it will enable intent-centric apps on Ethereum. I will focus on 3 main points: how it enables shielded transactions, how it supports general intents, and how it can interoperate with EVM state. Let's briefly recap what Anoma is and what the goal is we have. Anoma is a distributed operating system for intent-centric applications. It features a unique state model where a state is represented by atomic units called resources and an intent-centric architecture enabling users to present or express their preferences. The goal is to unify blockchains and infrastructure in a single development environment, and this is what operating systems generally do. They abstract hardware, graphic cards, hard disks, so that you can write your application without considering them, and we aim to do the same for Web3 infrastructure. the question this talk is now focusing on is how we can interface with existing blockchains and how we can do this now. So let's look at the graphic I took from our homepage, from the roadmap subpage. This is what we call the resource plasma, and can be found in the blog post that is linked there. So in this graphic, we see a couple of nodes. On the left-hand side, some nodes by users, then peer-to-peer nodes connected to them, and then some green solver nodes. And on the right-hand side, we see different kind of nodes. Those are settlement options. And here we see Ethereum mainnet, Optimism, and Arbitrum, and there could be many more. And there could be also ones that are, corresponding to other ecosystems like Cosmos or Solana or your own blockchain that you run. So users on the left-hand side would create and send intents to the network. Those would be gossiped to solvers, and then actually or eventually form balanced transactions that can be executed and settled on a settlement layer. So this is the part we were focusing on in this talk. And yeah, you can already see in this slide there are EVM smart contracts that do this job, and I will present you how this will work in more detail. What do we mean by settlement? First of all, we mean that we want to settle, verify and execute resource machine transactions. This means, which is shown by this graphic, that we consume resources, which is shown as red arrows that, then are consumed, and in turn, resources are created. And resources can represent different things, objects like coins or leaves or some potion. We have to publish state commitments for this transition that is happening, commitments to created resources and nullifiers of consumed resources. What we also eventually will do is store related data blobs. So maybe a resource contains some image that you want to keep, and this would be stored as a blob. And what we also want to do is transition state that might be outside of this resource machine or this protocol adapter, and this would happen through foreign function interface calls, so short FFI calls. And all of this is supposed to be done by the protocol adapter. So I will now present you the prototype I finished last week. It is a smart contract that maintains and transitions state, as I just showed. It's a smart contract written in Solidity, deployed on Ethereum, and it features a commitment tree, a nullifier set, and rudimentary blob storage. It's quite expensive, but still you can store blobs in it, and it allows you to settle shielded transactions using the RISC-0 ZK VM. So shielded means that you just see the commitments to the state, but you won't see the actual state as an outside observer. So you can have private applications. The protocol adapter will just verify the transaction, its validity and its balance, and then execute the transaction. And it also supports intents, which I will come to later. Current limitations of the protocol adapter are that it doesn't allow you to partially evaluate transactions later on, so everything must be already fixed and static, so you cannot add a timestamp later on currently. So it's a settlement-only protocol adapter, and currently it also does not support cross-chain transactions. But we will do this in a later iteration. So let's look at shielded transactions and how the transaction flow would look like. Let's start with a basic example. So there's user Alice, and she first of all owns 3 Apple resources and wants to give them to Bob. What she will do is call an Anoma application, which is written in Juvix, and Juvix applications or Anoma applications contain basically three things: transaction function, projection functions, and resource logics and resource definitions that are associated with this application. So in this case, there would be a transfer transaction function that takes care of consuming Alice's Apple and creating a new one for Bob. In order to do this and to convince the resource machine that will live on the right-hand side, so on the left-hand side we have the Anoma off-chain part, and on the right side the on-chain settlement part. To convince the resource machine on the right-hand side that everything is valid, there need to be proofs, and those proofs are generated with the RISC-0 backend we are developing. So the Juvix application would call this backend, compute proofs, and then output a transaction object in which everything is fixed. And this transaction object can then be given to the protocol adapter, which is deployed on Ethereum or some roll-up EVM chain. And it first of all would be verified by the protocol adapter, which calls the RISC-0 prover being deployed on the chain, and then executed. So on verification, we would check all the proofs, their validity, and also check that the commitment and nullifiers being part of the transactions don't already exist in the state. And if all this is given, then we will update the state and transition it. So the right-hand side is already implemented. On the left-hand side, we are working on the RISC-0 backend and making it available in Juvix. But we can already benchmark and test the Solidity contract I've written with mock proofs. And it's important to emphasize that those proofs have the same complexity and costs as the as real proofs. And here at the bottom, you see the interface of the smart contract. And it's literally just the execute and the verify function. The execute function also does a call to the verify function internally. So yeah, but you could also verify your transaction without executing it. And yeah, this allows us to do some initial benchmarks already, which I'm showing in this diagram. And on the x-axis, we see the number of resources being part and being processed in the transaction. And on the y-axis, we see the corresponding gas costs scaled down or multiplied by or divided by a factor of 10 to the power of 9. There are two important limits to consider. In green, we have the minimal gas cost that a transaction can have, which is just transferring the native token, which is 21k units of gas. And the red line is the upper bound or the limit, which is currently 36 million units of gas. And then we see two curves. The blue one shows the verify function cost, and the orange one, the execute function cost. And to give a rough estimate, so assuming we are on mainnet and the gas price is currently 1 giga away, a transaction with 10 resources being processed would cost around 6 euros currently, or $6 roughly. And that's already quite okay. Keep in mind that on other rollups or layers like Polygon or Optimism, Arbitrum, Base, the gas costs are about 2 to 3 orders magnitudes cheaper, and then a transaction would cost 6 or half a cent, 6 cents or half a cent. Just already for this first prototype, quite nice. However, like you can also see in the curves that the verification has a pretty large share of the cost overall, and then the execute function on top of this curve also has to write things to storage, which is the difference between the orange and the blue curve. So we can do some optimizations. First of all, keep in mind, we are using mock proofs, but the complexity is expected to be the same. And this is unoptimized and unoptimized contract, so we can have some improvements. Optimizations that we can make is aggregating proofs, which would lower the blue curve to a large extent and also reduce the slope a little bit or quite a bit. And we can also have more efficient data structures and lookups, which would affect the blue and the orange curve at the same time. Right. So this is like shielded transactions that are balanced, and now we can look at how general intents would work in this architecture. So we again start with Alice, having 3 Apple resources that she owns, but she wants to have 2 banana resources instead. So what she's doing is, again, calling a Juvix application and a swap function this time inside. This swap function would take care of consuming the 3 apples, requiring a signature by Alice that has authorized this consumption, and it would create 2 bananas for her. Then we would already, or again, compute the proofs for the resources inside and proving the compliance with the resource machine rules. But this time, the transaction would not be balanced. And this is what we call an intent. Intent is practically an unbalanced transaction which needs another counterparty to add in more parts. So here we introduce Bob, who coincidentally has 2 bananas and wants 3 apples. He also does the same thing. He calls a swap function, and an intent is created. And those 2 intents would reside in an intent pool, which is the gossip network that I showed in the beginning. So peer-to-peer nodes maintaining these unbalanced transactions in their storage, and then someone can find and discover those unbalanced transactions and compose them to form a balanced transaction. This could be the job of a solver. In this case, Alice and Bob can do it themselves. It's like really not very complicated, this intent, but if it would be more complicated, if there would be optionality or multiple constraints, let's say Alice wants at least 2 bananas or maybe 5 blueberries and some other resources, that would be maybe better job for a solver to find the most optimal solution for this intent. But here we assume that both just compose, or one of them just composes the 2 transactions, and then it can be executed. It's also important to note that, or keep in mind that we don't require a certain caller in the protocol adapter. So either Alice or Bob or Sally can execute the transaction as solver Sally. It doesn't matter who is calling the contract, so it's not bound to some of the authors of this intent. Right, and then the same thing happened as before. The transaction gets first of all verified, it's now balanced, and all the resource logics are fine, and it then gets executed. So this would be the flow of a general intent, so there's not much of a difference. The transaction then, I forget to mention this, sit in an Ethereum mempool, whereas the intent pool lives on the Anoma node side. Right, so now the last point of this presentation, interoperability with the EVM. What do we mean by interoperability? We are interested not only in writing new applications that can do new things, we also want to use existing things already living on Ethereum. And those could be owned objects that we all know, ERC20 tokens or NFTs, some other data, maybe there's some Oracle data, some price feeds or weather data or randomness that you might want to use as part of your intents or your application logic. There could also be registries with entries that you might be interested in, so curated lists or allow lists or prediction market outcomes, or simply accounts that already exist. So like Ethereum is doing efforts to enable or have more smart accounts. You could also control these smart accounts or make calls, read calls or write calls to these accounts, or even entire DAOs. So you could have your private DAO on Ethereum, like living in a resource machine, but having a proxy contract living on Ethereum. Like there was would be a private vote happening in this DAO, and in the end, some shielded DeFi transaction can happen out of this DAO. So this is already pretty great. So our goal is to read and write EVM state that is external to the protocol adapter and make it available in resource machine apps written, or like Anoma applications. So what we have to do here is to wrap this existing state, this existing external state in resources. Let's look how this would work. Again, Alice, this time she wants to wrap 10 existing Ethereum tokens wants to wrap her 10 existing Ethereum tokens in resources to make them available in applications she is using. So again, she would call a JUVEX application and a transaction function. This time it would be called the wrap function. And this wrap function would see this external call that or external state that Alice wants to access, and there would be two special kinds of resources. So there would be a wrapper resource and some corresponding token resource that should correspond to the 10 tokens that Alice owns on Ethereum. So we want to create this token resource, and the 10 tokens on Ethereum should be moved in an escrow until Alice decides eventually to unwrap it. Right, so again, this wrap function takes care of all the groundwork, creates this resource for Alice corresponding to 10 Ethereum tokens. Some proofs are generated that the resource logics are verified, and a transaction object comes out that in this case is again balanced and can be passed to the protocol adapter. The usual checks happen, but then something new happens. On execution, the protocol adapter will call a special wrapper contract that is associated with the token deployed on Ethereum. And this wrapper contract can only be called by the protocol adapter, and there is a one-to-one correspondence to the wrapper resource on the left-hand side. I will come to this in a minute. The wrapper contract in turn will make a call to the token contract that already pre-exists on Ethereum and will transfer the amount, like the 10 tokens that Alice is owning, out of her balance sheet and into the wrapper contract balance sheet. So this requires Alice first of all to approve that this can happen. Alternatively, you can also use permit 2, just a common thing today. Yeah, but like after you have authorized your balance being spent by some other contract, this is allowed to happen. So in order for this to be secure, we have to make sure that there is a one-to-one correspondence between the wrapper contract deployed to some address and the wrapper resource living in the resource machine state. And then there's a one-to-many correspondence between the token contract that pre-exists on Ethereum and the token resources that we create for Alice to then be used in applications. And the trick we are doing here is that we start from the resource of the token resource logic and enforce the presence of the wrapper logic or wrapper resource. The wrapper resource also enforces the presence of the token resource, and there is some referencing of the wrapper contract address and taking place, and in the end this ensures that this is legitimate and it cannot be that there's this correspondence that is then ensured. We don't need to go into the detail here. Right, so in the end what this allows is Alice to create a corresponding resource that has some correspondence to her balance on Ethereum, and if this resource can then now be sent to someone else, maybe to Bob, and this happens in the shielded domain, so no one can see that this resource or these tokens are being sent, and Bob can then decide to unwrap this resource to have again these 10 coins on his Ethereum balance sheet, and no one would see the origin of this. Right. So to summarize, the first point I was showing is that shielded transactions are now possible on Ethereum. We can have privacy-preserving applications. For example, you can have your boring counter that you increment shielded on the resource machine. You can also have private, or think of private auctions, private Oracle data, or private DAOs and private votes in DAOs as mentioned before, or even shielded DeFi transactions that can happen. We also saw that it's possible to have general intents with this EVM protocol adapter prototype. Already this unlocks multi-party applications between multiple counterparties, swapping things or providing services to each other, and generally counterparty discovery and solving is enabled. Lastly, we saw that there's the possibility to interact with existing state on EVM or Ethereum state, and that we can resources corresponding to state that we read, or even that is possible to write state through the protocol adapter. Also, we can control smart accounts or wallets living on Ethereum. One thing to mention is that in the upcoming Pectra upgrade that we are waiting, there is an EIP with the number 7702, and this allows you to delegate control of your externally owned account to a smart contract. And you could delegate control to some contract that the resource machine or some Anoma application has control over, and would be an interesting application. Or you could also have a DAO being controlled by an Anoma app. Right, and all of this is possible on EVM compatible chains and rollups, as long as RISC0 is deployed there. So the ZK prover by RISC0. However, we are also working on more resource machines. You will hear the talk by Xiang soon, or like after my talk, who is presenting to you the Cairo resource machine, and we will also have a transparent resource machine implementation for your application. Right. The key takeaway I want you to remember from this talk is that this is the first step on the road to mainnet and of the realization of the resource plasma that we saw in the beginning. We are now able to have shielded intent-centric Anoma applications that can run and interoperate with the EVM ecosystem on basically any chain or roll-up that has the ZK infrastructure deployed on it. Right. With this, I want to thank you and point to some more resources. We have docs, also specs, and art reports ordered by the layer of or level of complexity, so you can pick whatever you like. And now I'm open for your questions. Thank you.
All right. Thank you, Michael. Do we have questions from the live studio audience? Yes, we do. Yulia, please take the mic.
So you mentioned interoperability for EVM state, but about the interoperability between different resource machines, will it be different protocol adapter contracts, or is it the same contract that can just switch between resource machines? And also related to that, is it all for kind of the same chain, or do they kind of expect it to be on different chains? And to that also, how, well, maybe the last part I can wait until you reply first.
So the protocol adapter.
Can you restate the question?
Okay, so the question was if there can be, or if there would be the need to deploy multiple adapters for different resource machines. And the second question was if this would require to be on different chains, if I remember correctly. Or
Yeah.
So first answer would be, like, in the protocol adapter we can have different, we are just referencing a contract that is a verifier contract. So there could be, we are currently referencing the RISC0 verifier contract, but we could also reference the Cairo contract. Depends, of course, on the format inside of the data types and formats that we use, if there's interoperability. But there's nothing speaking against to having one adapter calling into different verifier contracts. And it depends, for your second question, if these verifiers have been deployed by, let's say, RISC0 or the Starknet people. But I think there's some overlap on some chains where both are deployed.
We could also deploy them ourselves, right? They're just smart contracts.
Yeah.
Or anyone else could deploy them with the code.
Exactly.
So the second part of the question, I assume right now protocol adapter uses just nullifier set, like set structure and like a Merkle tree commitment structure. But I think what we're planning for Anoma is a bit more complicated. What is the plan for that? Will it update the protocol adapter or what?
So, yeah, like first of all, you could pick different accumulator structures, but yeah, I think a smart move, and that's currently not the case, would be to have the storage in some external place and separate from the protocol adapter logic, and then you could just have a different adapter using the same storage, or you could also have an upgradable contract, which I would be not a big fan of, but yeah, like there are certain options, and this was just the very first prototype, and it's also not optimized.
People could also migrate state between different protocol adapter contracts reasonably easily, right? You can use the wrapper contracts or something to do that. So.
Yeah, it would have, like, of course, some costs connected to it, but yeah, you can also migrate your resources, consume them on one resource machine, move it to the other one, to another one.
So practically speaking, are we planning to kind of develop protocol adapter independently and then just create a new contract and migrate states, or are we planning to wait until the state design or implementation matures, or what is the plan?
I think there is not a fixed plan yet, so we can explore this the next weeks.
Okay, thanks.
Thank you.
Thank you. Other questions? Yes.
Great presentation, Michael. I wonder if briefly you can touch on your experience in starting to write applications in Juvix, given your background of a Solidity developer.
Yeah, so one thing that I particularly like is the fact that you just need to write your application once and don't have to bother with all the infrastructure like indexing or some ZK tooling that you have to write yourself. So it's all already, everything is there. Currently, writing Juvix application has some barrier that you need to overcome, and I hope that we can lower this barrier quite a bit. It's also a very new system, but yeah, I think it's much nicer than previous Solidity work I've done. Yeah.
Thank you. Yes, next question. Please take the mic. And those who are asking questions, you do not have to, but you can feel free to introduce yourself quickly as well.
Hey, I'm Rob. Yeah, thanks for the presentation, and great that you got the POC ready just in time. Something that wasn't clear to me, so you've got this as an instantiation on Ethereum that then verifies the state of the resource machine, and this then deals with assets, like Anoma assets. Are these always just assets that are specifically wrapped for that Ethereum instantiation, or are those general? And then my next question would be a concurrency of different VMs on different chains.
So you could have just state that just lives in the resource machine and has no connection to the outside Ethereum state. So if I have a counter, I don't need it to live in some external contract. It can just be a resource that I create in this resource machine and I increment it, or my multi-chat application that I'm using for some reason on some EVM chain. It could just live inside the resource machine state, and it would not need to have any correspondence to outside state on the EVM. If that answers the question, maybe it was pointing in.
Like nonces that you have for these resources when they're being accessed by different things?
So, yeah, nonces, like there is a commitment to each resource and a nullifier, so this uniquely identifies already the resource, and the shieldedness comes from the fact that you don't know the underlying content. So this commitment is derived from hashing the object, the resource object, and then this, the commitment is obtained, and you don't know by just seeing the commitments what the content is.
Got it. And then I guess the follow-up was with respect to concurrency. If you have multiple machines that are accessing this from the outside, if they try to spend the same commitment.
So concurrency, like there would be two transactions consuming the same resource. Yeah, like the commitment can only be consumed once.
Yep.
And then the second one would fail or revert.
Okay.
Like,
Yeah, I mean, with the protocol adapter deployed on Ethereum for resources which are controlled by that protocol adapter, it is Ethereum that determines the canonical ordering of transactions, just as it does for native EVM transactions. This just sits on top of that. We do have an entire cross-chain resource system called controllers, which describes how those cross-chain interactions and cross-chain resource transfers work. The protocol adapter does not yet implement that, but it will in the future.
Cool. Thanks.
All right, I think we've run out of time for questions on this presentation. Thank you again, Michael. And we will be, Michael will be followed by Shuyang talking about the Cairo resource machine in about 4 to 5 minutes. We'll take a short break.
Dvojku si vezme? Nebo
Jo.
trojku?
Kterou?
Dvojku.
I should use 2.
Just right now.
Yeah, no worries.
Okay,
Just waiting for signal? All right, welcome back to Anoma Research Day. If you are not here for Anoma Research Day, check your URL bars. Next up, we have Shuyang, who will tell you all about the Cairo resource machine. You just heard about the RISC-0 protocol adapter resource machine, but as you'll soon discover, the resource machine train never ends. Shuyang.
Hello, everyone. I'm Xuyang, and today I'll present the Cairo resource machine. I'll walk you through the basic transaction workflow, and I also will dive into technical details, especially the decision we made for Cairo resource machine and shielded resource machine. Okay, Cairo resource machine is actually a shielded resource machine instance built on the Cairo ZK VM, where we are using the underlying zero knowledge proof for compliance and logic proofs based on the ZK Stark system. And it starts from the Juvix Cairo front end. Provided by our Juvix team, and it ends up with the Anoma Cairo resource machine backend. All the things are available in our repo. Okay, let's start by the transaction workflow. First, the user needs to fetch the ciphertext and Merkle path from the service. Once they retrieve the encrypted resource and do the child decryption, and then they can figure out the resources belong to them. And then with the resources, they can further obtain the Merkle path to prove the resource existence from the cloud service. And then we already get the user already got all the data for the proofs, and then they also need the logic, right? We can, the users can use the Juvix language to write some logic programs. Then use the Juvix Cairo compiler to compile down the logic into proving key and verifying keys. Yes, for the users is that. Then let's move to the next step. For specific applications, users can compose or create some actions based on the data and the logic they already own. Generate the compliance proof, logic proof for each action, and then construct the initial transaction. Never mind, I'll introduce the details about the actions and transactions. I will not present the solving, the ordering, and the consensus protocol. They are out of scope for this presentation. So once the initial transaction is finalized or is solved, we can get a balanced transaction. Then we can generate a data proof. That means we can submit the transaction to the Anoma node. The last step, when the Anoma node receives some transactions from user or solvers, Anoma node validate the transaction. If the transaction is valid, update the state, namely update the commitment Merkle tree, maintain the Merkle root history, update the nullifier set, and store all the ciphertexts. That's the basic procession of the transaction. Then let's dive into the technical details. it's a standard resource struct. I'm not going to go over all the elements listed here. I'll just introduce some properties that are essential for Cairo resource machine or for shielded resource machines, like the logic reference. The logic reference indicates the hash of the predicate logic. Actually, it's a hash of verifying key. It is decided by the resource machine. Users cannot modify the logic reference hash. But for the label reference and the value reference, users or the developers can encode arbitrary data to the label and the value. And we recommend using the Poseidon hash to do the encoding, which would make the circuit more efficient. The quantity, eventually the quantity field will be converted to a finite field. So we also need a range check here to make it secure. Next is the ephemeral flag, which is a rule. It's a key element to achieve the intent. Intent resource is a special resource with a true ephemeral flag. And for the privacy consideration, we don't want to expose the ephemeral flag of resources. It means ephemeral resources and non-ephemeral resources are distinguishable. Later, I'll introduce the details. And here, and next, we also have the nonce to ensure the resource uniqueness. We also have the special constraints over the nonce to make it unique and to avoid maliciously set the nonce to create some duplicate resources. The last one is the random seed. Random seed is an important field for shielded resources. We need the random seed to derive some blunt factor to protect the resource commitment and resource nullifier. Then let's move to action. The action includes two main parts: compliance unit proofs and resource logic proofs. The compliance unit contains one consumed resource and one created resource. We want to make this more because it's good for parallelization and proof aggregation. Let's take a look at the witnesses and instances and the constraints in compliance unit proof. Overall, compliance unit proves that one resource is consumed correctly and one resource is created correctly. So the first constraint here is to check the nullifier integrity and the Merkle path validity. It corresponds to the witnesses of the first line and the instances of the first line. The Merkle path, we have the Merkle path to prove the existence of the consumed resource. And we also need the consume logic reference in the instances, because we need to further check the correspondence between compliance unit and logic later. For the created resource, we only need to check the commitment integrity. And the last constraint here is the delta integrity. Delta proof. Delta is the key element to prove the balance of a transaction. We'll talk about the delta proof in transaction section. Just remember all the elements here, because each element is valuable for the next for the next checks. Okay, let's take a look at how to make sure how to prove the existence of consumed resource. We don't want to expose which resource is consumed, so we check the root existence instead. There are some checks here to make the ephemeral and non-ephemeral resources indistinguishable. Like for ephemeral resource, the ephemeral resource will be consumed and created in one transaction. So ephemeral resource have a very short lifetime. So we cannot provide existence proof for ephemeral resource. And we also want to prove the indistinguishability of them. So the Merkle path, we provide a valid Merkle path and root validation for non-ephemeral resources. And we just provide a dummy Merkle path and an existed root for ephemeral resources, so that from public or validators' perspective, they cannot distinguish ephemeral and non-ephemeral resources. As we know, the nonce ensures the uniqueness, but a duplicate resource can also be created via malicious nonce setup, right? Trivial solution is to check the duplication every time when we want to insert a new resource to the Merkle tree. That's not what we want, right? We already have a proof. We want the proof provide as many constraints as the proof kind. So we use the consumed resource nullifier as the nonce for the new created resource to make it happen. As we know, the nullifier is unique, so the nonce is unique. So we can make the created resource unique. Then we can go to the logic proof. The logic proof is a deterministic application program written in JUVIX. It checks the context integrity, or the current resource integrity, and the existence of the current resource. It also includes verifiable encryption to make sure the receiver can decrypt resource. And there are other additional constraints decided by specific applications. Okay, let's talk about the verifiable encryption in logic proof. Why do we need verifiable encryption? In general, there are two kinds of encryption in blockchain, like out-of-band encryption and inbound encryption. Out-of-band encryption means that sender and the receiver need to create a security channel by themselves and share some secrets. That's not what we want. Inbound encryption means the sender is responsible to add the encryption to the transaction so that the receiver can decrypt it. But why verifiable here? In our MASP or Zcash project, inbound encryption is sufficient for them. But for us, especially when we introduce intent and involves multi-parties, things are different. Because, for example, we have three actors in one transaction. Alice creates encryption for Bob. Bob creates encryption for Carol. Carol creates encryption for Alice. It's a circle, right? Alice can maliciously gives out wrong encryption to Bob without sacrificing her own benefits, because Carol will may create a good encryption for Alice. The verifiable encryption here is a typical hybrid encryption scheme. We use the David-Hillman key exchange to generate a symmetric key, and we use the symmetric scheme to encrypt the plain text. So, because it's verifiable, so the receiver with the correct secret key can definitely decrypt the ciphertext. To make the encryption efficient, we are using the Poseidon-based symmetric encryption in Cairo circuit. After introducing the compliance and the logic proofs, we also need to check the correspondence between compliance and the logic. First is the logic reference correspondence. We already proved resources are created and consumed in compliance proofs. We also need to make sure correct logic execution or correct logic proof generation. If you remember, we have the yes, we have the logic reference in the instance of compliance unit. The resource machine would dereference the resource logic to get the verifying key to make sure the expected logic proof will be verified. If we want to achieve function privacy, here should be a logic commitment instead, because we don't want to expose the logic information. And then we also need to guarantee the logic context correspondence. it is basically a problem of context sharing between between different proofs. As the circuits have a deterministic constraints, so the circuits don't support a variable number of reading in inside. So we build a Merkle tree to share the context between compliance and logic proofs. That's all for the action. Then we can move to the transaction. The transaction contains a bunch of actions and a data proof. The data proofs ensures the balance and the integrity of shielded transaction. We can take a look at the data structure, which is constrained in compliance unit. We can get the data from the compliance unit instance. The R resource in is the consumed resource quantity multiply consumed resource kind. The kind is derived from resource logic and the resource label, which is unique. This part is for created resource. Here we also need a blend factor to protect the privacy of the data. If and only if it's a balanced transaction, we can generate a data proof, namely a binding signature. From this equation, we can find out if it is balanced. The sum of the compliance unit data, like this part, will be eliminated. It's a sum of these parts, and the private key would be the sum of the blend factor. It's exactly a key pair for signature, so we can create a standard ECDSA signature for the transaction. That explains why only a balanced transaction could have a data proof here. Our next step, as mentioned, we still need to do the child decryption for the ciphertext. In next session, Yulia and Enric will introduce a new technology, shielded state sync, would make the child decryption easier. And there are many proofs in the transactions in actions, so the proof aggregation would significantly improve the efficiency. And we also want to protect the privacy of logic. So we already have a framework for function privacy. I hope next time we can share more details about the function of privacy. And I also will show you some examples we have in our repo. it's a standard Cairo compliance circuit written in Juvix. It proves the integrity of commitment, nullifier, and the data. It's quite neat and concise. Thanks to Juvix team's work to make it happen. We can also take a look at the witnesses we need for the compliance proof. Input resource, output resource, nullifier key, and the Merkle path. Users and developers don't need to worry about the structure, because the resource machine will generate the JSON format automatically for you. We also provide a powerful Juvix Cairo library for developers. Here we can take a look at the logic example. Like we load the self resource, nullifier key, and the Merkle path under the verifiable encryption. It's also very easy for developers to create a resource logic in Juvix program. Yeah, I think that's all I have today. Hope you enjoyed. Let's see if we have some questions.
All right, thank you. Do we have questions from the live studio audience? Keep them concise, Michael.
Thank you for your presentation. You mentioned proof aggregation as a possible way to lower the costs. In which part would you then start with aggregating proof, and where would it be the easiest?
I think the compliance proof aggregation would be the easiest way, because the compliance circuit is a fixed one. We can easily aggregate the compliance proofs. The logic proofs are different based on different applications. We may have some problems, but it can be solved. Yeah.
I have a very basic question. Given that you have a Cairo implementation, but also a RISC-0 implementation, does this imply that you can just basically have any kind of proving backend that you want with the resource machine?
Yes, exactly.
Modulo engineering details. Any other questions from the live studio audience? All right, then we have one question from the internet, which is when testnet. I will take this one. So we have something currently live that we are calling a DevNet, as in it's intended for developers, and it is really early stage. There are already some great docs on the DevNet at docs.anoma.net, and you can find the code, for example, which Xuyang just referenced, is fully open source, so you can look through it and start playing with it. Developers, beware, this is early frontier territory, and there may be great beasts lurking in the wilderness, but also lots of interesting things to check out and play with. So try that out, let us know what you think. And of course, further testnets that are perhaps a bit more user accessible will follow later this spring and throughout the year. All right, thank you again, Xuyang. We are going to take a 5-minute break, and then we will come back with shielded state synchronization, which you do not want to miss. See you soon. Welcome back to Anoma Research Day. If you were not here for Anoma Research Day, you were in the wrong place. Check the URL bar. Next up is shielded state synchronization. What is shielded state synchronization? You are about to find out. This presentation will be a hybrid joint presentation by Kike or Enrique and Julia. Kike will be joining us remotely. Hopefully the internet does its magic and you see all the video happens just fine. If otherwise, let us know. All right, Kike, take it away.
Okay. Hello everyone. Yes, you can. So yeah, in this talk I'm going to be talking about how to synchronize shielded messages with fuzzy message detection. In this project we started in the last quarter, and many people have been involved. You have the names at the bottom of the slide. And yeah, let's get it started. Let's see if this is working. Right. Okay, so the problem that we are trying to solve or to make it more efficient is how can we recover shielded messages. So this is in general in modern decentralized systems where you want to exchange some information and you want to make this exchange anonymous. There is like a very clear blueprint that it was started with ZCAS to achieve these anonymous exchanges of messages, and it's by the senders encrypting their messages wherever they want to send to some receiver with a key private encryption scheme, and then publish this ciphertext, which is the so-called shielded message. They publish this in a public pool, for example, a blockchain. But then the question is, since this shielded messages reveals no information at all about the identity of the receivers, then how can receivers retrieve these messages, right? So this problem, for example, arises in the multi-asset shielded pool in the Namada blockchain, where when you want to implement shielded transfers, and as well in Anoma, in the Anoma protocol, when you want to synchronize shielded states or resources. So in the previous talk, Xuyan has been explaining how the shielded resources are generated. What's the encryption scheme, the hybrid encryption scheme. So we have these two possibilities. Later on, in the second part of this talk, Julia is going to be explaining more on the Anoma particularities, but I will focus on the general statement where we have just a shielded message and we want to be able to retrieve it. Okay. So the naive solution or the free solution that comes to mind is, well, what the receivers can do. They can just download the entire set of messages from the public pool and then try to decrypt all of them to see if the content makes sense. The problem with this is that, yes, receivers needs to download the entire set of messages. So this is bad in terms of communication overhead. And as well, they need to run the trial decryption and on all the messages. Usually the ciphertexts are going to be encrypted with some public key encryption scheme, or if the encryption scheme is symmetric, then to derive the decryption key, you need to do public key operations, so that's expensive. So there is overheads in terms of computation and communication if we use a naive solution. And people has been looking at how this can be improved. There are a number of ways to do this, and one is going to be it's done using fuzzy message detection. There are other approaches like oblivious message retrieval or private signaling. Also, some ad hoc solutions in set cases implemented in some SIP, as well as there are other solutions. We focus on this one because we think it's more efficient. So at the early stages of this project, we were looking at different possibilities with oblivious message retrieval, for example. But the thing is that it requires FHC in oblivious message retrieval. So yeah, the technology there is not super fast. With FMD, with fast message detection, we can do it very efficiently. Also, although there are some controversies between privacy and efficiency, we can get a hold on this and leverage between, well, get a good between privacy and efficiency, as we will see later. Okay, so what we're going to use to make this retrieval of shielded messages more efficient is fuzzy message detection. First of all, a cryptographic primitive that is used to outsource detections of messages to servers that are untrusted. So we do not trust the detection server. Right. So the idea is that the sender, he generates some flags using the receiver's public key, and then in the public pool, in addition to the shielded message, it attaches some flag to this message, and then detect the pool, and using the detection key of the receiver, detects whether the flag has been generated with the public key of the receiver, and that means that the message is addressed to the receiver. Okay, so in a little bit of more detail, the main point of FMD is that detection is probabilistic. So what this means is that if the flag has been generated with the public key of the receiver, and we run detection on this flag with the detection key associated to this public key, then the detection is always going to say, yes, this is a flag, it's a correct flag. So this is a true positive. But if the detection is run in a different flag that has been generated with a different public key, then sometimes the detection is going to say, yes, this is a correct flag, even if it's not. So this is a false positive. The good thing about this is that you can create the anonymity set out of this. So basically, the set of messages that are not addressed for the receiver, but the detection outputs yes, they are addressed to the receiver, is the set of is the anonymity set of the given message. And for this to work, we need to ensure that the server, he doesn't distinguish between true and false positives, because if he can do that, then there is no anonymity set at all. So one key property for FMD is detection ambiguity, and it's a security property that protects against the servers, the entrusted servers that run the detection. In summary, the important thing is that the false positive rate at which the detection is executed, if it's high, then it gives you more privacy because you have a larger anonymity set. And if it's low, then it gives you more efficiency because you filter more flags, more messages. So at the end of the day, the receiver will need to execute less decryptions. So there's this trade-off between privacy and efficiency. Okay, so this is all what I wanted to say about FMD. And now I'd like to quickly introduce the system that we've been designing in the last 3 months. So the main design criteria that we have in mind is that we want that the false positive rate that is known to a detection server, we call it the leaked rate, is high. So that means that there is more privacy towards an untrusted server. But at the same time, we want that the effective filtering rate at which receivers can get the messages is low. So there is more efficiency. They need to run less trial decryptions. At first, it seems that this is contradictory because it's not possible to set some false positive rate on the detection server, but at the same time have lower filtering rates. But this can be resolved if we move to the threshold setting. So now we are going to leverage multiple detection servers. So in this setting, these goals can be achieved. Okay, this is more or less the architecture or the overview of the solution. So in this case, in the picture, I hope you can see it well, more or less. So we have 3 detection servers in this setting. The receiver starts by generating a key pair of public and secret keys. The public key is just publicized, so every sender can use it to flag messages, and then the secret key is passed through multi-extract algorithms that generates the detection key for the different servers. Once the servers get the detection keys, they can start filtering messages and then send their outputs back to the receivers, who is going to combine all these filterings and run the trial decryption on the combination of these filterings. So the key parts, or the parts that are novel in our solution, is the multi-key extraction and the combine operations. Both are run in the receiver side. So I'm going just to explain quickly about how these 2 components work. So for the multi-key extraction, as I said here, in the standard FMD, in a standard FMD scheme, there is just one single detection key. So from a secret key, you extract one detection key. We generalize this to, from a single secret key, we can extract multi-detection keys, as well as, instead of passing just one rate at which the detection key is going to be able to filter, we pass 2 rates. One is the leaked rate and the other one is the filtering rate. The requirement here is that any coalition of no more than T servers, where T is a parameter as well that is passed to the multi-extract algorithm, can infer any information at all about the other detection keys that they do not control. So this means that they cannot, you can put a lower bound on the filtering, on the filterability of this coalition of these servers. So this is a generalization that we described with respect to the syntax and the semantics of the FMD scheme that appears in the original paper. And we build a scheme just by doing very, very minor modifications to the FMD2 scheme that is present in that paper. The other operation that is important is the filter combine. So now the receivers, once they get all the filterings from the different detection servers, the idea is that the receiver is able to combine all these messages somehow. And then the output of this combination, it looks like as an output that was filtered at a lower rate. So at a rate PF, which is also the other input that we give to the multi-extract algorithm. So these 2 rates are decided by the receiver and are chosen, and it gives you this balance between privacy, where the leaked rate is what is known to the servers, and the filtering rate is known to the only to the, well, is achieved only by receivers. One important thing to note here is that the combination, the combine operation is public, so everyone can do it. It's efficient, and that's nice. I mean, that's what we want. Otherwise, it wouldn't be important. But everyone can do it. So there is no secret information involved when you combine, when the receivers combine. And this means that we need to be careful and protect what is sent between servers and receivers, because anyone getting that information can filter at lower rates as well, and lower than anonymity set. Okay, so these are the core. These are the 2 core components of the system, but we also look at 3 different nice-to-have features that we can also implement and actually are implementing. So one is key expansion, the other is key randomization, and the other one is doing key rotation on the server side. So for key expansion, the thing is that the scheme that we are using, the FMD2 scheme that we are basing our solution, it has public keys that are very large. The question is, how can we make these keys shorter. There is a challenge, which is public derivation. So if we make the public keys short and send these public keys to senders, they need to be able to later expand these keys into a fully fledged FMD public key. So this derivation must be public because the senders, they do not have the secret keys. And these two combinations is what makes things a little bit challenging. So one approach would be using BIP32 like ideas in which actually there exists work on this. The idea here is that you start with a set of master key pairs, and then you take linear combinations on the secret key pairs to derive the keys. That's fine, we could do that. We are not doing it this way, but that's one possibility. Okay, so that's one of the features that we can implement, key expansion. The other one is key randomization. So here the idea is similar to stealth addresses, in which you are able to randomize. If you can randomize the FMD public key, then the receivers can emulate different identities. So for each randomized public key, there is one identity. But at the same time, we want all these identities, all these public keys, to be controlled by the same secret key, which means it's also controlled by the same detection keys given to the servers. So this is good because it simplifies the life cycle of the detection keys, and also I think it has a good impact on privacy, because at least for the notion of unlinkability of it helps to avoid trying to link messages that are sent to the same entity. And the last feature is server-side key rotation. So here it is important for forward privacy. So in principle, users, I'm just kind of rushing because I think I'm running out of time. So for server-side key rotation, the idea is that the users, they rotate their detection keys with the servers, but they might forget to do it. So ideally, should be the servers who can, do this key rotation on the background, and they can do it without any action from the user. The idea here to achieve this is that flags for messages are generated using an extra FMD public key, which is owned by the detection server or servers. So if this is possible, then it's only needed to rotate the detection keys owned by the detection servers. We still have detection keys for users, but there is one extra detection key that is only controlled by servers, and that's what is being rotated. And once these detection keys are erased, of course, at some moment in the future, if this server is corrupted, then it won't be able to find identities of messages from the past. So that's why it's interesting. Yeah, I hopefully did not rush too much. This is all I wanted to say. I'm going to pass the control to Julia, and at the end of her presentation, there will be time for questions. So I will be as well available for that. Thank you.
All right, now we will start part 2 of the shielded state synchronization presentation, in which we will introduce tea. Over to you, Leah.
Yeah, so I'm going to first talk about how to expand this solution to Anoma, and then about T's. So the need to extend this protocol for Anoma is because Namada and Anoma are kind of different. And Namada supports simple transfers, where a sender just sends something to the receiver, and Anoma supports programmable transfers, where there is a solver. And solver makes everything complicated, and specifically it makes us need to have a verifiable FMD. So just to explain why in more details, here is a diagram. So there is a sender. Sender wants to send something to the receiver in an encrypted form, and the receiver has the key, but the receiver doesn't know what to decrypt. So what the receiver naturally would do is to try to decrypt everything. which is not exactly efficient. When the receiver realizes that, it becomes very sad. So the solution would be to have an FMD server and to augment transactions with some flag ciphertext. And the server just tries to decrypt the ciphertext that tells to if it's designed to be received by the receiver or not, and then forwards everything to the receiver. And the receiver just enjoys the results. So this is how it is for Namada. But for Anoma, we have a solver in between. So the sender asks the solver to do something, and the solver, in principle, is not incentivized to send exactly what the sender wants. So here, the sender wants to send a love letter, but solver decides to send something else and just throw the love in the trash. And in the end, the receiver is very sad because the receiver doesn't receive the love letter and everything is sad. So to fix that, we need to add additional field to the transaction that proves that what the solver did is actually correct, that the solver encrypted the flag ciphertext correctly and the transaction is correct and the receiver receives the love letter and everyone is happy. And yeah. So this is how we extend FMD to work with Anoma, verifiable FMD. And to make it even cooler, we add TEs. We add TEs to FMD server for both Namada and Anoma, so it's not specific to Anoma case. I just didn't want to change the diagram. So what is TE? It's a hardware solution for isolated code execution. And it allows to protect against malicious host environment. So in case you send your sensitive data to someone you don't exactly trust, TE can help. And it's supposed to provide confidentiality and integrity. So for confidentiality, we need to keep detection keys secret from the host. Detection keys are used to determine if the transaction is for the receiver or not. Then we also would like to keep the detected messages secret from the host. And generally, we would like to keep secret everything from the host if we can. Some things we can't, but ideally as much as we can. And integrity allows us to make sure that the FMD protocol is running correctly, so that we are running the protocol we are saying we are running. And so you might have heard about TEs and heard that they might be not exactly secure. And there are some attacks on TEs, and they work more or less similarly. So they leak data from shared memory, like cache, or from controller-related memory, or via hyperthreading, and can leak both application-specific data, so the data that we share with the server, and also TE keys, so the keys that make the solution secure against the malicious actor. And leaking these keys allows to break integrity of the TE. And this pattern is kind of similar for all TEs that we checked, namely SGX, TDX, and AMD SEV. Yeah, I mean, with details changing. But if we analyze attacks in terms of what we can do about them, we can divide them into two categories. Some attacks that can be mitigated by developers, which we don't care much about because we can mitigate against them. And then there are attacks that require microcode update. And this is much worse because it requires the TE developers to update the firmware, which is super slow, and we're depending on someone else, right? And this will always probably be the case because it's a hardware solution, so we're always dependent on who develops the hardware and firmware. And so microcode update requiring attacks can be divided into the ones that require kernel mode access, so the operating system privileges, or user mode. Luckily, most of the attacks do not work in user mode, so if the attack works in user mode, it kind of means that anyone can do that who has access to the same machine. So if we assume that the operating system is not malicious, then we can mitigate against all of the attacks, all of the kernel level access attacks. So the thing here is that the most relevant attacks require the operating system to be malicious, the attacks we want to protect the most from. But at the same time, TEs are kind of designed to protect against that, right? So like if operating system is malicious, then T is supposed to help, but the attacks, well, you see. So what we do, we assume that the operating system is not malicious, and therefore we automatically protect against most of the attacks within our model. Of course, in reality, it's not exactly like that, so if the operating system is malicious, all of the guarantees that we have in our model do not apply. So the question is, do T's actually help then? And the answer would be yes, because T's increase the cost of the attack. So it's similar to having a lock on your diary. Maybe if it's not locked, someone might read it just for fun, but if it's locked, it's just not worth it, unfortunately. Yeah. So there are more challenges with T's that we have, namely reproducible builds, tooling, availability of T's, and because of all of that, reduced practical integrity benefits. So in details, the way integrity check works in T's is basically it's a signature over the T state, and for that you need a binary of your application. It's included in the state, right? So it implies that whoever verifies the signature compiles the application from the source code and then checks the signature against this compiled binary. And this kind of assumes that compilation works the same way on different machines at different times and possibly on different settings. And this might not be true, especially for T's. And this is related to the second issue, that the tooling you need for T's is not very mature, and you basically need to develop your own things for more or less everything. And because of that, well, not because of that. So like some of the T's are based on virtual machines, for example. And because of that, you kind of need to develop the whole thing yourself, because you need to integrate your application in it in a way that is just inconvenient. So right now it's not super mature. Another issue is that availability. So cloud providers support access to T's, but the providers I checked, they support a limited number of T's, some of which are custom and might not be so interesting to us, for example. And they also provide limited access to these T's, so proper testing is not even possible. But like, we can get our own servers to test. Obviously, one server per T, because we can probably have different T's on the same server. But the problem is that we're not going to be running this. This will be run by some other computationally powerful entities, right? And they will have the same problem. And basically, depending, like, if they go with cloud provider option, they have limited access to T. If they go with their own servers, then they might have different servers, different T's, and so we need to make application work for multiple T's, but we know that tooling is problematic, so we need different tools for different T's, and different entities use different T's, so it's like, it's a lot. And because of all of that, we have actually reduced practical integrity benefits, because it's all a little bit annoying, and nobody wants to put their code in the whole T. For example, we have the whole FMD protocol, and if we put it in the T, then we get guarantees about the whole FMD protocol, right? But it's extremely complicated, because we need to interact with the indexer, and it's just difficult to do from the T. And so we put the detection part of the protocol in the T, but then we basically only get confidentiality for the detection keys and integrity for the detection part. But we do still communicate with the operating system, against which we would like to have protection and integrity guarantees, which are not provided if the operating system runs the protocol. So yeah, there are a lot of problems. On this optimistic note, I would like to hear your questions. We are about to release a report. It's currently in review. We also want to produce a academic paper with enhancements that Enrique mentioned, and security analysis and benchmarks. And we also have a prototype on GitHub, and we have a bunch of posts on Research Forum that discusses all of that. Now I'm ready for the questions.
All right, thank you, Yulia. Questions from the live audience? Yes, Jamie.
Testing. It's working. Okay. Yulia, thank you very much for that lovely talk. I have two questions. One is, just to be clear, are T's worth it? And the second question is, I once went to a talk on T's, and I remember the speaker said it's useful to get different T's to talk with one another. So he said similar things to you, that the friction is if you want to communicate between the outside world and inside the T, but if you can encapsulate everything in different T's, then they can communicate via confidential channels. So I was wondering if, presumably you've considered that, but you didn't mention it, so how does that fit in? That concludes my question.
Yeah, so I'll answer the second question first, because it's less philosophical. So yes, it is easier to make T's communicate to each other, but the problem is that we want users communicate to FMD server. So if we use T's communicating to each other, it means that users have to have access to T's. And so the question would be, do they have their own T, or do they use cloud provider, or like how does it work? So it's like basically we want to make it easier for the user, and if we make the user to use T's in order to make it easier, it might result in the opposite result.
Thank you.
Yeah.
And when I asked if T's are worth it, I didn't mean it philosophically, I just mean, are they worth a bother?
I know. I thought about it. I expected this question, honestly, and this is not exactly a theoretical question, I think, because we have another problem that we try to solve with T's called private solving. So just a short introduction. Private solving is about solving intents in a way that the solver doesn't see what the intents are. And so we came up with the conclusion that T's are probably the most viable option. And right now, I don't think so, honestly. So T's were the most viable option compared to MPC because it's easier to use, but now it doesn't seem that way. So if we put a solving strategy, for example, in T, we cannot put the whole strategy because it's even more complicated than the FMD protocol. FMD protocol is quite simple compared to that. So I don't think T will give us that much benefit, and I'm not sure what to use instead, to be honest. So I'm definitely not feeling as positive as before about T's, to be honest. But maybe with advancements in tooling and availability and like increased popularity, it gets better. But I feel a bit skeptical about the whole microcode update situation because I don't think it will go away ever.
Other questions from the studio audience? Isaac.
Thank you. I'm curious about alternatives to fuzzy message detection, especially if we're willing to make the same kind of threshold assumption that one of our intervening servers from someone in this group is honest. Are there other private information retrieval techniques that we could consider?
I think so. I think there are other techniques that we can consider. I think fuzzy message detection is the most promising in that sense. But one thing that we were discussing on the forum is something that Chris proposed as shielded state synchronization that is, I think, push-based or pull-based. Yeah, push-based. So basically where the receiver is kind of notified about receiving something via mixnet, so you basically always know what to decrypt. So instead of trying to decrypt everything or like delegating it to someone, you kind of get to know what to decrypt. But I think other solutions similar to FMD are not that kind of helpful.
Other questions from the live audience? Any internet questions? Okay, then thank you again, Yulia and Kike. So now we will take a slightly longer break, and we will resume in 25 minutes at 15:15 Central European Time. See you then. Don't miss it.
test, test. Can you hear me?
All right, welcome back to Anoma Research Day. If you are not here for Anoma Research Day, you may be in the wrong place. Check your URL bars. We are now starting our second track, Distributed Systems Delights. And Isaac here will kick off the second track with Store, Order, and Execute. What does that mean? You're about to find out. As a reminder, you can always send us comments and questions in the chat, and we will forward them to the speaker after the presentation and do our best to answer them. Thank you for tuning in. Isaac, take it away.
Thanks. I'm Isaac. I'm a scientist at Heliax working on Anoma, and I'm here with an overview of how our Anoma chain architecture will work, and we'll get to dive more into details of part of it. I'm hoping that people will ask questions as they come up because I'm going to cover a bunch of different stuff. The idea overall is that we want to build an efficient, high-performance architecture for chains with native support for Anoma resources and transactions, as well as the ability to run on-chain post-ordering computation. I want to start fairly zoomed out to explain how I think about blockchains and why we're making some of the design choices that we're making. The idea behind a blockchain is to maintain a replicated state machine. The machine, which is replicated across all the validators, starts in some initial state, and each transition is a transaction candidate that updates it to a new state. Usually, individual pieces of state have well-defined permissions on when and how they're allowed to update, such as only Alice can deduct money from Alice's account. These are defined in code that has to be checked each time the state changes. These checks are validity predicates or smart contracts or stuff like that. Usually, we want our blockchains to be highly available. That does mean that they should be easy to read if you have permission, but it also means that everyone should be able to commit transaction updates. We want high throughput. The really tricky part, however, is that we also want high integrity. We want everyone to agree on the replicated state machine even in the presence of failures. So, for example, Comet BFD does these things. It produces a basis for maintaining a replicated state machine with high availability and high integrity. Why do we think we can improve on something like Comet BFT? Well, to begin with, we're hoping to support pretty generic state machines, but our requirements will end up being a little bit different from Comet's. So if anyone out there is interested on a new engine to run your state machine on, perhaps our architecture will prove right for you as well. Certainly, we want to be able to run the Anoma state machine on our chains, but we want the same core concepts and even most of the same software to be used to be able to be used for quite different state machines. So, some improvements we think we can make. Comet's throughput is fundamentally limited, and there are a couple of reasons for this. One is serialized execution, which is pretty normal for blockchains, but puts a fundamental limit on throughput regardless of how good your distributed system is. When I talk about serialized execution, I mean that Comet executes each transaction candidate from start to finish sequentially, not just in some equivalent order, but actually in sequence. This serialized execution means there is no concurrency. It puts a fundamental limit on how many transaction candidates could be processed, even if all of the distributed system stuff were completely free. Essentially, all applications on the chain would have to be able to run on a single CPU, almost by definition. Ideally, we would execute transaction candidates as concurrently as possible while preserving some kind of equivalence to a serialized execution, like high-performance databases do. We want to preserve an execution that's serializable, that is to say, equivalent to a serial execution. So within each transaction candidate, reads and writes will be consistent with the global order of transaction candidates. But when transaction candidates don't actually touch the same parts of state, we should be able to compute them in parallel, even using multiple machines in each validator if they're up for that. To do this, we have to break up state into multiple substates. We assume that the state machine state is divisible into key value pairs. And we require that each transaction candidate is labeled with which substates it may be reading or writing. And any transaction candidate which tries to read or write outside of those labels would fail, much like one that runs out of gas. The execution engine could then run multiple transactions concurrently, even on separate machines, updating their separate parts of state. And we're leveraging existing work in high-performance databases here. Specifically, the gold standard is a database property called serializability. The idea is that for the purposes of reads and writes within each transaction candidate, it behaves as if they were executed in some one-at-a-time serial order consistent with what is determined by the chain. But under the hood, we actually compute them faster than that, taking advantage of parallelism when possible. This is going to involve an execution engine where validators have multiple concurrent processes, and the mempool and consensus engine forward them the relevant information so that they can execute transactions and update some state. In fact, we're pretty careful to avoid any single process having to touch any part of all transaction candidates. The way Comet does leader block proposals also creates a bottleneck that damages throughput and latency. The authors of the Narwhal and Tusk paper found a major bottleneck in is that each Comet block, along with all the transaction candidates that it contains, has to be broadcast by the proposer of the block to all the other validators. This broadcasting can be a limiting factor for throughput and a significant latency problem as well. Ideally, we distribute transaction candidates out of band in a less centralized manner, and consensus would only need to agree on references to collections of transaction candidates that we know are already available. Their answer was the Narwhal mempool, which they published in 2022 at Eurosys, which allows validators to store an arbitrarily large structure of transaction candidates while consensus only has to periodically order signed references. Narwhal lets us decouple that consensus latency or bandwidth from throughput, which is really useful. The authors of Autobahn, a couple of years later, however, point out that if you're going to do consensus outside of the mempool DAG anyway, then we can relax that requirement slightly. So for our next prototype, I propose that we borrow heavily from their concept of data lanes. Eventually, we'll want to expand our functionality and be able to handle atomic transactions that update state on multiple instances, so across multiple chains. This requires changing the definition of what it means to agree on the state machine, since different chains have different validators. We will enable a new technique, which we call chimera chains, but which is outside of the scope of my talk for today. At a high level, our architecture looks something like this. Transaction candidates from users and solvers and the like arrive into the mempool where they are stored. They're ultimately ordered by consensus, and using the information from mempool and consensus, the execution component updates the local replica of the state. Our mempool should use something like Autobahn's data lanes. It stores batches of transaction candidates so we know that they're available, and consensus then only needs to work on references to those batches. This is how we address the block proposal bottleneck. Our consensus layer then establishes a total order of these transaction candidates. Later prototypes can adapt heterogeneous Paxos, which will enable Chimera chains, which will help address cross-chain transactions. And the execution engine will then need to read that total order from consensus and the transaction candidates from the mempool and actually update the state machine with as much concurrency as possible, addressing the serialized execution problem. So these are the main components. Each of these could be its own talk, but for the moment I want to drill down a little bit into the mempool and specifically what I'm proposing for our next prototype. So a transaction candidate comes in and validators need to store them. Rather than in some amorphous mempool set, we're going to start ordering them right away. Sort of. Each validator has a set of worker processes, some of which, one of which is considered user-facing for this validator. The user-facing worker receives transaction candidates from users or solvers, or things outside of the chain, and orders them into batches, each of which references a previous by hash. All of the other validators will maintain replicas of this validator's user-facing mempool worker. Naturally, these are not perfectly up to date. User-facing workers can pass along transaction candidates as soon as they receive them, but there will be at least some transmission delay between the user-facing worker and its replicas. Recall that the plan is to get to a place where consensus proposals include references to the mempool, but don't have to include transaction candidates themselves. That said, we can't propose something that isn't actually available. The chain would effectively be crashed if we had committed to say that the next transaction candidate was this one and you can't read it. So in order to produce provably available proposals, we need to produce availability attestations. First, when a replica stores a whole batch and all of the batch's ancestors, it votes, informing the user-facing worker that it has stored it. User-facing replicas collect votes until they've heard from at least a blocking set, some member of every quorum, or if you like, more than a third of the stakeholders. This means that for all the failures that the chain can tolerate, some live participants will be holding the batch. When a user-facing worker collects enough votes, it can create an availability certificate. And various signature aggregation schemes and threshold cryptography schemes could be useful here to make the certificate small while proving that it contains an appropriate set of votes. Finally, the user-facing worker distributes the availability certificate to the replicas. And these are what we'll ultimately use in consensus. So within one validator, when the consensus component looks at the mempool component, it sees something like this. There are a bunch of workers. One of them is user-facing and the rest are replicas of other people's user-facing workers. And each of them has some batches, and some of those batches have availability certificates. In particular, if anything has an availability certificate, all of its ancestors are ultimately available as well. It's a product of the voting system. So a consensus protocol should look like this. It's a most recent, or consensus proposal rather, should look like this. It's a most recent availability attestation from each worker. This means that the size of a consensus protocol, or consensus proposal, is fixed. It's the number of validators times the size of an availability attestation, which gets us around the proposer bottleneck. It also means that anyone who sees the proposal can be sure that everything in it is available. Ask enough other validators and you will be able to obtain copies of all of those batches and all of their ancestors. It also means that if consensus takes an arbitrarily long time to get around to proposing for whatever reason, we can accumulate an arbitrarily large data structure of transaction candidates ready to be proposed without having to increase the physical size of the proposal that gets transmitted in consensus. So if we zoom out a little bit, we'd see that these data lanes, with an ordered series of cuts across all lanes, chosen by consensus every so often, all we need is a deterministic function that orders all of the transactions before each cut, but after the previous cut, to be appended to the total list of transaction candidates. We can even keep that order consistent with the order in each lane. Effectively, we're interweaving the lanes in some deterministic way or another. Now, there are some nuances to Autobahn's approach. To begin with, nothing actually prevents Byzantine nodes
from forking their user-facing worker's data lane, making it into a tree. Replicas might notice, producing evidence of malfeasance, but in the meantime, the chain has to be able to survive such a thing. Fortunately, at least for what we've talked about so far, these trees don't turn out to be a problem and the same rules apply, but the details are a little bit complicated, and I'm not going to explain them. So that's how I think we should handle storing most of the ordering of transaction candidates for our upcoming prototype. Now for this prototype, we're not focusing on doing Chimera chains, so in principle, an arbitrary off-the-shelf consensus will do, but it still has to be a classic Byzantine fault-tolerant consensus that can deal with stake-based voting. Now, I want to dig a little bit deeper into how each validator actually executes that sequence of transaction candidates determined by this process, and then maintains its copy of its own state. Recall that what we're really going for as an improvement here is throughput, and that we're trying to maintain this serializability guarantee that instead of executing things in some serialized order, we execute them concurrently, but in some equivalent manner. So, what kind of state machine can we support? Just a quick reminder that state machines in this context are the abstraction over the blockchain that we're trying to really care about. There's some kind of combined rules in every state machine about how transaction candidates can change that state. So EVM is one example. The Anoma state machine has its own rules. We don't want our architecture to be completely specific to the Anoma state machine. We want it to be able to support lots of state machines, but they do have to be able to support some kind of API. So let's start with what the limits of that have to be. To begin with, the execution engine is going to store the state machine's state. We require that the state has to be a key value store. We can have some structure to the keys. They can have ordering or nuances, but that's another story. These are the keys that we'll use to identify which pieces of state each transaction candidate touches, and so we can safely parallelize. Each state machine also has to define an executor. An executor, in this case an executor function, is simply a deterministic function that takes as input a transaction candidate and the state before that transaction candidate, and outputs the new state after the transaction candidate. It is this executor that ultimately specifies what the transaction candidates have to be, or what language they're written in, or anything about gas, or rules about how they transform state. Oddly enough, the executor is allowed to have side effects. It can send information out over the network or whatever, as long as that output state is uniquely deterministically determined by the input state and the transaction candidate. But that's another story. Unfortunately, this isn't enough to run things concurrently. We're going to need to tag each transaction with a label that the system can understand, specifying a set of keys that the transaction candidate might read and a set that it might write. Solana does something like this under the hood. Then, when we run the executor with that transaction candidate, it's only allowed to read keys in the read set and write keys in the write set. This way, when two transaction candidates don't conflict, we know that we can safely parallelize them. So that's basically our API for what it looks like to plug a state machine into this engine, and what that state machine and those transaction candidates need to implement. So let's think about how that state is actually stored. We'll start by looking at this from the perspective of one state key in the execution engine. Now there are some known transaction candidates which read or write the resource stored at this key, or the value stored at this key. Now it's totally fine for a transaction candidate to read and write the same value. None of these do for no particular reason. For now, let's assume that these are totally ordered by consensus. We have already somehow determined a total order. And we have this nice happens before relationship that completely serializes this timeline for this key. That happens before relationship, by the way, I mean, that's the thing that mempool and consensus are built to do. That's their whole purpose in life, and we've just assumed that it's already done. So let's look at another key as well. And of course, the main guarantee that mempool and consensus give us is that this timeline will be consistent for every key. It's the same order of transactions. We won't get cycles in the happens before relationship. That would be bad. So for example, suppose we had this simple system with 4 keys and just a whole bunch of transaction candidates, and they're all fully ordered by consensus. So the basic execution rule is that you can execute a transaction candidate if all the transaction candidates that happen before it are already executed. And when I say execute here, I mean calculate all of the values it writes by running the executor function for the state machine. Well, we already have some parallelism just by having broken this up into keys. We can run these 2 transaction candidates first concurrently, and then we'd run this one and this one. And we'd have some more parallelism when we run these concurrently, and then we can run this and this, and so on, and so forth. A little concurrency here, a couple more, and then we finally executed all of our transaction candidates. But there are a few optimizations we can do to get even more concurrency and process all of these transaction candidates quicker. First of all, we only really have to totally order the writes, and then order the reads in terms of which write they happen before and which write they happen after. Whether or not another transaction candidate reads before or after we read doesn't really change the value that we read. So this example execution would start the same, but then right here, for example, we'd get to do these 2 concurrently, which we weren't able to do without this optimization. And if we execute a little more, then here again is some more concurrency we wouldn't have been able to do before. And here, so now we've executed fully, and that's ordering with respect to writes. The next optimization is a little bit more complex. We can plan to store all of the values written to each key at each point in the timeline so that we can still read old values. This would be multi-version storage. This would mean that while we still have to wait to read a value until after it's written, we don't have to wait to write something just because someone else needs to read the old version. The old version is still in storage. So right at the beginning, we can execute all 6 of these transaction candidates, and then 4 more, and then 5 more, and then these 2, and we're done. Things are really starting to move along quickly now. There's one more optimization I want to talk about. This one won't be in our next prototype. It's a longer-term goal. It comes from the mempool transmitting partial ordering information to the execution engine before consensus has decided on the total order. If there's enough partial order information in the mempool, if there's enough structure that we can add in there, then we can imagine that we have a partial order on some transaction candidates. Our happens before relationship could be extended to a may happen before relationship that includes all possible orderings. And the idea here is that eventually consensus will come along and refine this to a total order. And some of these may happen before relationships can be removed. The last thing we'll need is some kind of timestamp before which we definitely know all the transaction candidates that are going to write to a key. And this requires some mempool structure, but it happens in, for example, Narwhal. We can derive this from mempool DAG structure. It can also happen because of a consensus decision. After this time, it will be very hard to run a transaction that has any reads because we can't be sure that something won't come along and write just before that read, something we don't know about yet. So our execution could start right away on these transaction candidates. Note that the write-only transaction candidate actually can always execute immediately. It doesn't depend on anything in state, so I guess we can just go ahead and execute its executor function as soon as we hear about it. Then we can run these transaction candidates that we've fully determined the values that they read, and then we could run this one, and finally these. But notice that until consensus finishes ordering things, this is as far as we can go. The values that these transaction candidates read aren't completely determined yet. Specifically, this transaction candidate is trying to read the blue key, but it's faced with a write-write conflict. It's not clear which of the prior transaction candidates wrote last, so it's not clear which value this transaction candidate should read. This transaction candidate has a read-write conflict. It's not clear whether this read happens before or after this write, so it's not clear what it should read. And this transaction candidate has a transitive conflict. It's trying to read a value written by a transaction candidate that's stuck on a conflict. These are actually all the types of conflicts we have to worry about, and they emerge kind of neatly from thinking about this may happen before relationship. And then, of course, when consensus comes along and decides which of these writes happens before the other, we can get rid of some of our may happens before relationships. A write-write conflict would be resolved, and so this transaction candidate can execute, which of course resolves the transitive conflict as well, and this transaction candidate can execute. Eventually, consensus would totally order everything, and every transaction candidate will execute. There's actually one last neat trick we can do in this kind of setup. You see, read-only transaction candidates don't affect other transactions. These are operations that don't actually write a new state, but in most respects, they're the same as any other transaction candidate. Thing is, no one ever has to wait on them to run. That means that they can bypass the mempool and consensus entirely and just be placed directly into the execution engine timeline, which can execute them when all their dependencies are available. And that's exactly how I believe a client read should be thought of. A validator can execute a read request from a client at any time without pumping it through the rest of the system. Gather signatures from a quorum of validators doing client reads, and you've got a light client. Question?
Isaac, how much of what we have just seen came out of your brain, and how much of it came out of the literature and prior art?
A huge portion of it came out of the literature. In fact, a lot of it is directly inspired by this paper, Calvin DB, published in Sigmod 2012, which proposed a system with a separate ordering engine that decided on total order of transactions, and then sharded state system that updated from there. We've modified the design slightly to avoid redundant computation, but it is largely based on existing best practices.
Okay, and is there a algebraic account of what's going on here?
I don't know that there is one that would meet your standards of algebraic.
So, for example, up to about halfway, we were talking about some kind of monoid-like thing where commutativity... does the word commutative appear in this paper?
Actually, I kind of suspect that it doesn't, but there are similar works on executing before total order is known that have notions of commutative. In fact, they have notions of right commutative and left commutative.
Okay, okay. Thank you. Thank you.
So I want to talk a little bit about how we implement this concurrency in terms of software processes. Like I said, our big inspiration for this setup is Calvin. And primarily here we're talking about how we pass this partial order information and transaction candidate content from the mempool into the execution engine. So let's imagine that the mempool has stored a transaction candidate, which is labeled. And meanwhile, the execution engine has partitioned its state that it's storing into some processes called shards. Here I've drawn one key per shard, but it could be multiple. And for each key, its shard maintains a multi-version timeline. Well, first the mempool has to communicate admittedly partially ordered timestamp for this transaction candidate to each shard that the label touches, and let that shard know if the transaction candidate reads from that shard or writes to that shard. Shards don't need the transaction candidate text, but they do need to keep a timeline of resources, or a timeline of values along with which transaction candidates are reading and writing when. Then we need an executor process. This is where we actually run that executor function from earlier. We could maintain a pool of these or boot up a new one for each transaction. Conceptually, it doesn't really matter. The mempool communicates the transaction candidate to the executor process, which actually interprets it and runs the state update function. Note that for efficiency, we might want to co-locate that with one of the shards involved if we're spreading this out across a distributed validator. We also need to establish channels of communication from the read shards to the executor process, as well as from the executor process to the write shards. What this means is that when the read shards have computed the values that this transaction candidate will read, they communicate those to the executor, who then computes the values to write and communicates them to the write shards, who store them. And of course, these are, there are some optimizations here too we could introduce. And in fact, I believe we should use lazy reads so that not all values need to be transmitted, and special writes for the probably common case of I'm choosing not to change the value here. Finally, the executor is done. We no longer have to store it. We don't actually have to store the transaction candidate anymore as far as the execution engine is concerned, just the values that it output. This actually connects to garbage collection, which is a whole other area I'm not going to get into just now. Pretty much everything else, including interactions with consensus, is about communicating that ordering information to the relevant shards. There's a lot more detail I could go into, but I've gotten to dive into a couple of the main components. I'd love to talk about consensus and cross-chain transactions, but they're a whole other thing, and our next prototype is not focused on those, so I think I'll leave it there. We are building an engine to support running a replicated state machine. We've talked about using a mempool to store and start to order transaction candidates, and using consensus to order only references into that mempool. We've talked about running transaction candidates efficiently and in parallel while maintaining serializability. And we've discussed the major components of our architecture with mempool workers for transaction candidate storage, shards for state storage, and executor processes to run transactions. Next up, I believe Anthony will give us a closer look at what the actual implementation code for those executor processes look like. So before we transition, are there any questions?
Thank you, Isaac. Are there questions from the live studio audience? It's all clear. You could implement it yourself. Yes, Patrick.
Great presentation, Isaac. You covered a lot of ground. I wonder if you could just maybe in a couple sentences talk about Autobahn a little bit, and some of the improvements over Narwhal.
Yeah, so just a second. Autobahn was a paper published at SOSP last year, which looked at a lot of the DAG mempools and started to ask how much can we strip these down. The Narwhal mempool is built assuming, well, it is built to do a number of things, and it maintains a number of guarantees. And Narwhal maintains, Autobahn maintains fewer of those guarantees, mostly in exchange for speed. And to some extent, simplicity. So if we assume that you're going to run an extra consensus that's not somehow included in the mempool DAG structure, which is what the Tusk part of the Narwhal and Tusk paper is, then we just have to figure out what the consensus proposals are going to be. And if we allow those consensus proposals to not just be a single point in the DAG, but a cut across the DAG, for which they reason that we're already sending messages that scale with number of validators and size when we distribute things in the DAG anyway, then we can actually maintain a number of validators, number of data lanes that don't necessarily have to cross-reference each other. And then it became a question of how do you deal with disobedient or misbehaving validators who don't necessarily produce a well-formed data lane, which I mentioned here, but did not go into details of why that turns out not to be the end of the world.
Wait, take the mic.
Can you clarify, is a data lane, does it correspond to a specific validator or to a key?
Right. So in a sort of our translation of Autobahn terminology, each mempool each validator maintains this collection of mempool workers, one of which is user-facing. That user-facing worker is what's generating their respective data lane. It's a sequence of batches of transaction candidates. So if you were to look at all of those together, you would see a collection of, if everybody were behaving properly, linear chains of data that can grow at independent rates because they're not interlinked.
Other questions? Yes, please take the mic.
Yeah, thanks for great presentation and very enlightening talk. So here in this picture, perfect. So in the context of MEV, you usually try to get top of block or similar. So here I'm not quite sure what is the best strategy for like being like last before next consensus or something. So if I have this, if I see in this picture these very long chains in between these lines, what is the incentive to submit early because later I might be sniped or something, or like how does this work?
So usually, well, technically a lot of different incentives for different markets, but it all will depend on whether you're trying to be early or late in the collection of, in the ultimate sequence of transaction candidates, and what the ordering function used to translate this graph of batches into a sequence of transaction candidates is.
Which in principle could involve introspection of the transaction candidates, right?
It could. You could have that introspect. You could have it do some kind of pseudo-random organization. You could have it try and respect some kind of first come, first serve if you're trying to encourage people to race to get their transactions in as fast as possible. That doesn't even have to be the same across every instance. That could be a per node or per chain choice.
It could theoretically be an auction, a first pay.
Yeah, absolutely.
Other questions from the live studio audience? Any questions from the internet? Okay, I have a question, which is in this concurrent execution architecture, assuming that only a finite number of transaction candidates conflict with each other, is there a throughput limit other than the number of servers, mempool workers, whatever that validators are willing to run?
If the validators are split across, if the validators each have enough hardware under their belts, then if we do it right, there is no fundamental limit to how wide they can parallelize.
Infinity transactions per second. You heard it here first. All right. Thank you, Isaac.
Thank you.
Let's just accelerate. Yeah. So coming up in 5 minutes will be Anthony on the implementation of some of what you just saw in this talk.
talk. I'm pretty good. How are you today?
Do a little bit of your, hand movement demonstration.
Okay, I'm here to talk about executor shards. First, we need to start with the big picture. This is going to be... Okay.
Welcome back. This is Anoma Research Day. If you are not here for Anoma Research Day, you are in the wrong place. Check your URL bar. We are in the middle of the second track, Distributed Systems Delights, and the next presenter will be Anthony talking about the Executor and shards. You just heard a lot about the, let's say, the theoretical architecture, why we've designed the database system this way. Now Anthony will talk about how we're actually implementing it. Take it away.
Sure. So I'm going to be talking about the executor and shards as they exist in the Anoma specs. So this relies on an engine abstraction. So you can think of the executors and the shards as being these sort of objects that exist on the network, and they operate by sending messages back and forth to each other, the worker as well. So before we get into the details, let's look at the big picture. Shards implement a KV store, a key value store. Transactions are just a series of reads and writes, so that's it. And transactions contain a program which issue the reads and writes. The executor engine will actually be running this program, and as it runs, it'll send these reads and writes as messages over the network to the shards. So before we get into the executor and shards, everything is started by the worker. For the purposes of this talk, I'm going to assume that there's only one worker, so we don't really need to worry that much about consensus. It receives transactions, and its job is to order the transactions. Whenever a transaction is created, it'll give it a timestamp, which we also think of as the transaction's name, and we can broadly also think of it as the name of the executor engine itself, although they are separate pieces of data. The actual name is more like an address. Each transaction can read and write to a key only once. This will become more relevant later on. And importantly, when a transaction is received, that is when an executor is actually spawned. So the executors don't exist until the transaction occurs, and they are made for their transaction. Additionally, whenever a transaction is made, the worker has to send messages to all the shards, telling those shards what reads and writes are going to be made beforehand, and those are called locks on those reads and writes. So the executor, this is the state of the executor. We see on the left the configuration. This is the data which does not change over time as the executor runs. And on the right, you see the actual state, which changes over time. Part of the executor configuration is its timestamp, the actual the executable, which is the program which is being run. It also remembers the set of lazy keys and lazy writes. This is the same data that the worker sent to the shards in the first place. And at the bottom, it also has information for the worker and the original issuer of the transaction. On the right, you see the stuff that changes over time. We have the program state itself, as well as the completed reads and writes. And at the end of an executor's life, it will bundle those completed reads and writes into a message, which it sends back to the worker. So this is the type of the actual execution step. So it takes that executable, which does not change, whatever the current program state is, and it takes a key value pair, which was received from a shard, and it returns a result. So the result can be a string, which is just an error, or it could be a pair consisting of the new updated program state, along with a list of either reads or writes. So we can have as many new reads or as many new writes as at once, or the list could be empty, in which case it has no reads and writes. One thing to note here is that it takes a single key value pair as an input. Even if the program itself wants to have multiple, it needs to actually only take them one at a time, and that's because responses from shards are received asynchronously, so you can't guarantee that they'll all come in. But you can design your program state to accumulate read and write pairs before it actually sends any any messages out, in which case, most of the time, its response will just be an empty list. Let's look at the details of the behavior. So let's start on the left. So this left occurs when, so the executor itself only ever does one thing. And that's because it only ever expects to receive a read message from a shard. It never gets any other input. It never actually gets any input from the worker because the worker tells it everything it needs to at spawn. And so this diagram shows the beginning of what happens when it receives a read message. It runs that program type that I showed before, and it executes it one step. Oh, that's one step. And the result, it could be an error, in which case it'll crash, and I'll show you what happens in that case later. Otherwise, it is a success, in which case it updates the program state, and it tracks the completed read. So in that case, it'll update its list of completed reads in its previous program state, and it can either halt or not halt. If it does halt, it creates a success message, which actually has a similar result to it crashing. Otherwise, it gets a response back from the program telling it that it should continue reading and writing, in which case it parses. On the right, we see the actual parse diagram. So where everything in that list of responses, it's either a read request or a write request. If it's a read request, what we need to actually determine is that whether or not it's actually valid. So it should be in the list of locked reads and lower locked writes if it's actually valid. If it's invalid, then it's just thrown away. Otherwise, it's packaged into a message that can actually be sent over the network. Then we collect all of the generated messages, and then we send them to all of the different shards. Another detail that's worth talking about is how the executor knows what shards it should send to for keys. For the moment, we just assume that it's a part of the network that you can just look up what shards are associated with what keys. And so that's not something the executor knows exactly, but it's something that it can tap into just being part of the network. So if the executor halts, and so this is what happens in case of either a program crash or if it just succeeds and it halts. So what we need to do is compute all of the stale locks. So these are the reads and write requests which were allocated, which were locked before, but were never actually used. And so what happens is that messages are sent and they have a little bit that tells the shard whether or not it's a dummy read or a dummy write. So if a shard receives a dummy read, that means it doesn't actually send a response, and we'll see that later. But all of these locks need to be cleaned up. We need to tell the shard that these reads and writes aren't going to happen anymore. In the case of an error, these are all cleaned up, and then we send a message to the executor branch basically saying that we errored out. And then if we finished okay, then we send the same message but with a success. Okay, shard state. So the core part of the shard state is this DAG structure. And the sort of diagram that was in Isaac's talk can be thought of as like the sum total of all the DAG structures across all of the different shards. So there are 3 main components of the DAG structure. 2 at the bottom are the heard all reads and heard all writes, which are timestamps. So these are actually sent to the shard by the executor. And these tell the shard whether or not it's heard all the reads or heard all the writes. And in the mempool worker, it'll keep a list and a history of all the transactions that'll have occurred. And whenever it gets a response back from an executor saying that it's halted, that means it knows that it's halted. And you can look at all of the timestamps of all of the executors which have so far halted, and you can say that the most or the latest consecutive one is the last one that's going to be executed. And so we're not going to see any reads and not going to see any writes before then. And so it will send messages to the shards indicating that, and the shards will keep track of those timestamps in heard all reads and heard all writes. So, and we'll see how those are used later. The actual core DAG structure is this map going from keys and timestamps to this key access data structure. And a key access contains the read status and the write status. So this tells us whether it's going to be read, whether it has actually been read. If it were to be read, what data would be there, or if there's no actual data there yet. And so we can see the actual particular. So one thing to note about this key write access is that there's both a read status and a write status. And the reason is because a single transaction can read and write to the same key if they want to. However, every transaction can only ever read or write once to a given key. It cannot do it multiple times, and that's just enforced by this definition of this data structure. If we look at the details of the read status, we'll see that it has a Boolean telling whether it's been read, also whether or not it is eager. So the way that eager reads work is that when there's enough data accumulated in the transaction history to be sure that the most recent write before this read is there, then we can just pick up that value and send it off immediately. We don't need to wait for anything. So if a lock is eager, that means that read message will be sent immediately when it's able to. And we also have this executor ID, and this is there so that the shard actually knows what engine it's supposed to send this read message to whenever the eager thing is evaluated. We have the write status, which may or may not have data yet. And we also have this may write Boolean, which indicates that it's possible that it may not actually be written to, in which case it has to be cleaned up by one of those stale lock messages when the executor that locked it halted. Okay, so there are 4 messages that a shard is expecting. The first one is this acquire lock message, which comes from the mempool worker. It basically just looks through this DAG, it looks through this key access map, and it just adds all of the reads and write statuses with has been read set to false and with the data set to none. And it just goes through for every single read and write lock in the message. So when it gets a write message, it asks for whether or not the write lock actually exists. If the write wasn't actually locked before, which means it doesn't even appear in the key map yet, then the message is just rejected. It asks whether it's valid for the right type. So this is essentially indicating whether or not it's a has write lock or or will write or a may write lock. If it's invalid, then it'll just reject it. If it passes those tests, then it'll update the DAG. It'll write whatever data is in the write message into that that data section there, so it won't be empty anymore. And then the shard will look for any eager reads which can now be read. So it'll just look for all of the time-stamped eager reads afterwards. That occur immediately afterwards, and this is important to it is important to remember those timestamps for heard all writes and heard all reads. So in order for an eager message to actually be sent, it has to be before the current heard all writes. And the reason for that is that if it isn't, it's possible that a new write might eventually be inserted into the DAG structure between whatever the most recent write was and the current eager read. So if the eager read is after the current heard all writes timestamp, then it won't actually send a message. Okay. Next is a read message, which is sent from the executor. And so there's a couple of different checks. It checks that the timestamp of the reads is actually after heard all reads, otherwise it's invalid. Asks if the read lock exists, same logic as before. And if it passes those tests, then the read is marked as actually having been read. And we see if the actual flag is true. So if the actual flag is not true, that means it's just a dummy read, in which case no actual response needed to be sent. Otherwise, the response is actually sent. Otherwise a response is looked for. So in that case, again, it looks to see whatever the most recent write is, and if there is a valid write that it can return as a response, it finds that, sends it off as to a message. Otherwise, it fails because it can't do anything. And this is the update CNAL action. So this is sent from the mempool worker whenever the mempool worker actually gets an update on the most recent pending consecutive transaction. And there's, of course, writes and reads. If it's a read, then the barrier just updates. If there's a write, then that means that there are potentially new eligible reads or eager reads which can be sent out. So when that happens, it looks for all of the possible eager reads, sends them, if possible, to any executors that are waiting for them. Otherwise, it completes. And that is the end. That is the current implementation as it stands.
Thank you, Anthony. All right, are there any questions from the live studio audience? Yes, so Rob first, then Patrick.
Dumb question from the beginning. So each transaction can only read and write once for a particular KB. Is that globally, like for a particular block, all transactions for that key, or just that transaction? Every transaction can only...
so the key can be written to multiple different times. A specific timestamp can only read or write once. And that is just because the transaction is associated with the time that it was actually sent.
So if a transaction needed to write twice or something, then I would split it up into two transactions.
Exactly.
And then so if there's like reordering from the executor for these transactions, one of them may depend on the other. Do you have any guarantees there that or some way to indicate that this one precedes that one?
So it would have to be, in this current setup, it would rely on whatever timestamp is assigned by the executor. So the problem you're saying could happen based on how I've described it, but that's going to be based on how the mempool worker is implemented and how it interacts with whoever orders the transactions. That's a bit out of scope of this. But
okay. So whoever orders it has flexibility to reorder them, and then it would fail?
Yeah, in principle, you could modify the interface. So you could say, make sure this happens after this previous transaction, but that's up to however the mempool worker is implemented.
I mean, I think this goes back to Isaac's description of the ordering function, right? Okay. Pretty much. Patrick.
Great presentation, Anthony. I noticed in the code snippet that you showed Executor engine ID. I was curious if you could elaborate on what an engine is.
Yeah, so this is going to be elaborated in different levels of detail into upcoming art reports. But the way that I generally think about them is that they're just sort of encapsulated pieces of state that exist on a network, and they can just asynchronously send each other messages, and whatever messages it receives will cause it to update its state. There's a bit more structure to it in terms of how the messages have to be formatted and how things are allowed to respond to it. But those details I don't think are super important for this specific application.
Do you expect that the role of the executor will be low resource requirement, like anybody can execute locally, or do you think that it will be something that will require running a node in a data center?
I don't see any reason why, in principle, it couldn't be executed locally. I mean, it's just an interface at the end of the day.
Thank you. Any other questions from the live audience? Any online questions? No. Okay, I have one question.
Sure.
Which is, how does all of this relate to the resource machine?
My current understanding is that the resource machine would be implemented on top of Nakma. And so if we go to here, I guess it's just not here, but if we go to this execution step, this step function is a parameter to the executor. And so there would have to be some step function that interprets like a Nakma executable and a program state and the key value for as input to the program. And this program would implement the resource machine under one of those descriptions. And things like the Merkle tree and the nullifier set would be implemented as particular data structures inside this particular program state for this particular machine model. So this is sort of generic over any kind of choice of virtual machine. And what I understand is the resource machine would be an example program that you'd plug into this.
Makes sense. All right, thank you, Anthony. We will take a 5-minute break and come back with the last presentation, but certainly not the least one, in the Distributed Systems Delights track, which will be Jamie on a declarative way to specify distributed algorithms. See you soon. bar. We are in the Distributed Systems Delights track, sadly not yet a Swiss chocolate offering. Maybe soon. And the last but not least presentation in this track will be Jamie talking about a declarative approach to decentralized or maybe distributed or something algorithms. What might that mean? Jamie, take it away.
Christopher, thank you. Thank you all for coming. I'm delighted to be here. Thanks for organizing. And who can tell me hands up if you know what tablet is? You all know what's a tablet. Christopher, what's tablet?
Something that the ancient Sumerians used to track their accounts.
Or it's a Scottish sweet. Would you like to take a piece of... Jan, do you want to start off? So the person who set me up is called Jan McGregor. So you need to have one. Please take a piece of tablet. I have more, so don't worry about running out. It's sugar, sweetened condensed milk, and butter. It is fantastic, and it's Scottish. Okay, right. So, guys, I'm here for your understanding, including the people in the internet. Hello, everyone on the internet. So please, if you have a question, just interrupt. Let's practice that. If you have a question, put your hand up. Please put up your hand. Hände hoch, please. Wonderful. Okay, well done. So you do that, and I'll stop and I'll take the question. Okay? Hands up if you understand. Thank you so much. Okay, so decentralized algorithms are algorithms that run across a system of participants without central control. And I was taught to distinguish between decentralized and distributed. Michael, could I have my water, please? Thank you. Distributed algorithms still run on multiple machines, but they might not necessarily be centrally controlled. I might be lax and use the word synonymously. But either way, hands up if you think that decentralized algorithms are hard. They are, right? I mean, they're really properly difficult, aren't they? They're hard to design, hard to understand. Hard to understand has been a biggie for me because I came to this field from the outside. I didn't do my PhD in decentralized algorithms. So just trying to understand them has been a major barrier for me and hard to verify, right? Of course, blockchain consensus algorithms are decentralized. They're not the only example, but they're the example of interest here. Academic examples include Paxos and Bracha Broadcast. We will treat Bracha Broadcast in this talk because it's smaller than Paxos, just so you know. Oh, by the way, Christopher, when do I need to be finished, please?
You have easily an hour.
Okay.
So don't worry about it.
Thank you. Yeah. If you start to look restless, I'll know. I've got my clock here as well. So I've been studying, I've been thinking, how to represent these algorithms declaratively as axiomatic theories, thus capturing their logical structure in a new high-level way. Out of interest, who has an idea of what an axiomatic theory is? Hands up if you have an idea, yeah? So axioms are things that are supposed to be true, right? So that's where the idea is we write down some stuff that's true, like Euclid did, right, about triangles and stuff. Only now we're doing blockchains instead of geometric shapes. I personally have found this, I've written very helpful, invaluable. Right? I could not understand distributed algorithm to the extent that I may at the moment without having done this stuff. And these techniques have already found useful application. We have already used these things to find 2 errors in the heterogeneous Paxos protocol. So not only has it been helpful for me, it's been helpful for at least one other person. Right? By the end of this talk, I hope you'll have a flavor of declarative Bracha Broadcast. If you want to scan the QR code here, you'll find 71 pages on declarative Paxos, which I think was too much for a 1-hour talk. So, but it's the same thing. It's just a question of scale, right? The difference between a mouse and an elephant is just a question of scale, right? Biologically, they're the same organism. So it's a similar relationship here. Has everyone who wants tablet got tablet, by the way? Yeah? Anyone tabletless? Have you run out, Patrick? No, you're good. Too late. Okay, well, they're there if you need them. For the avoidance of doubt, this is not a talk on TLA+. TLA+ is a logical specification language, but it's not declarative in the sense that I intend. TLA+ is used to describe executions of an abstract machine, and the abstract machine is what I will jettison in this talk. Right, we'll be talking about executions of distributed algorithms without any executions. It will retain the essence of the algorithm, but there's not going to be an abstract machine. This is not a talk on applying TLA+. Any questions? Okay. So let's start with a toy protocol, which I will call toy. We'll fix a pair of a set of participants. You can all be participants if you want, okay? So you can all be in P. And a set of quorums, which I might call open sets. Hands up if you're familiar with the concept of quorum, please. Hands up if you're not familiar with the concept of quorum. Right, okay. Oh, you're waving your hand. Okay, so a quorum is like in a voting system. If the whole quorum votes yes, then the vote is deemed to have been won. Right? And more technically, a quorum is what I call an actionable coalition. An actionable coalition is a collection of participants with the resources to act independently of the rest of the system. That's really important. So I cannot lift this table on my own, but I reckon 2 people could. So for the purposes of lifting this table, an actionable coalition is any 2 reasonably strong people. And they can lift the table without having to involve anybody else. They don't need permission, they don't need to tell them. That's an actionable coalition. And this is precisely the notion of quorum here, and I identify this with a topological notion of an open set. But you can forget all of that for now. I'll come back to it. Okay? So, toy has 3 stages. First of all, any participant may propose. What do they propose? We don't care because this is a one-value simplification of praxis, so they just propose. And if a participant receives a proposed message, then it can accept. And if a participant, having broadcast a proposed message, receives an accept message, then it decides. This is a toy protocol. It is deliberately useless. Its purpose is just to look like all the other more complicated protocols. Okay? How am I doing for pacing, by the way? Is it good? Yeah? Okay. We're going to model toy using modal logic. So I need to spend a slide explaining modal logic to you. Then there'll be another slide of background on 3-valued modal logics, and then we'll get back to toy. But let's just talk about modal logic. A logic is a thing with predicates that take truth values, right? It's raining is a predicate. A modal logic is a logic whose predicates depend on time or space. So it's raining is secretly a modal predicate, but you don't see it, not in the syntax. But if I say it's raining now, this is obviously modal, because the value of now depends on now, right? And similarly, if I say it's raining here, this is visibly a modal predicate. So modal logic just means logic with predicates that depend on where and when you are. Which means that in order to evaluate a predicate to a truth value, you need a context of what's called a possible world. Terence, you have a question?
What are the constraints on what time and space?
It's fine. What are the constraints on what time and space is? That's up to you, Terence. You can have any space-time you want. It's just an arbitrary set of possible worlds. But traditionally in modal logic... Literally any set, yes. But typically modal logics are used to talk about space and time. But that's a cultural thing, right? If you come from flatland, Terence, I'm not saying you do, but if you did, then you'd be, you could have 2-dimensional spaces. That would be absolutely fine. Okay. My pleasure. Please, let's give Terence a round of applause. Thank you. We need more audience members like you, Terence. So it's raining somewhere is modal, and now we're having a bit of fun because this is a modal operator, this diamond. Diamond means somewhere. And now you see this is a proper modal predicate. Diamond raining is true if somewhere it is raining. If there is a possible world where it's raining. And it's raining everywhere is also modal. Box raining means it's raining everywhere. So when the other day Ray complained that the stand-up wasn't a stand-up because not everyone was standing up, literally the first thing that went through my mind was, yeah, but you don't know if it's diamond stand-up or box stand-up. That's literally what went through my mind. So for toy, the possible worlds will just be participants. So stuff is true and false at a participant. More formally, I thought it would be helpful to put in some notation. Phi is a predicate, W is a possible world, which in this case will just be a participant, and the meaning of phi is a function of the possible world. Or to put it another way, the truth values are obtained by combining a predicate with a possible world, and this is a symbol for doing it. Okay, can I carry on? Yeah? Just for fun, yes, Terence.
Okay, let's have fun now then. So if there are no constraints on it, but could you place a constraint that that space-times must come from, say, some category, and then your modalities actually are just the adjoints of base change, whatever they are in that category?
If you want to, yes, absolutely.
And everything goes through.
This is out of scope for this talk, but yes. Just to be clear, yes. Oh, sorry. Terence was asking what categorical models there might be of modal logic, and I said yes, I am sure they are, but that's out of scope for this talk. Thank you. Julia.
Just a stupid question. So you said that participants are places, right? Could they be times?
Absolutely.
Okay.
So the thing, one way in which Paxos is harder than Bracha Broadcast is everything in Bracha Broadcast, there's no real need for time. Whereas with Paxos, you have rounds.
So my understanding is that participants are places because you have time and place, and you need to pick something to be participant.
No, it's much simpler than that. The modal logic doesn't actually care what the possible worlds are. So for the purposes of this example, the only notion of locality is the participant, and that's it.
So there is some meaning. It just sounds like time and place are kind of meaningless variables, but you picked place, not time. So I thought, is there a meaning behind that or not?
No, there's no meaning.
Okay.
No, thank you. It's just conditional on the. So for Paxos, we literally need participants and natural numbers. For Bracha Broadcast, we can do just with participants. That's a structural thing about what we're going to do. Does that answer your question?
Yes.
Thank you. Okay, 3 truth values. Hands up if you've seen 3-valued logic before. Oh, wow, cool. Bit higher, please. Right, and you are not sure, which means you're returning B, which is a 3rd truth value. So you'll be familiar with true and false. The 3rd truth value, B, I might call that Byzantine. It can stand for I'm crashed, I'm not sure, I'm hostile. Anytime you don't want to answer true or false, you return B. And I will find time for just a little story here. My wife wanted a new front window for the house. And she said, can we get a new front window? And I gave what I call the male monosyllabic grunt. I went, uh-huh. I go to a conference, I come back, guess what? They're literally installing a new front window. And I said, I didn't authorize that. And she said, yes, you did. I said, no, I didn't. She said, I asked you and went, uh-huh. And I said, yes, the uh-huh was prevarication. It was B. So she'd interpreted B as true, which is actually a reasonable interpretation of B. Yes?
Your wife says hi from the live stream, by the way.
Oh, hello. Remind me to only tell nice stories about that. Thank you. God, you can't escape anywhere nowadays, can you? Thank you. Okay, so. You see, I blame my wife for that. It's thrown it. I'm fine, thank you. Thank you, Jan. we need to name our sets of truth values. So singleton T will be correct. Singleton T is true. TF is correct. That means you haven't crashed and you're not Byzantine. Guys out there, please keep it down. Be good. Thank you. And TB is valid. Anthony. Oh. Okay, I'll blame my wife for that as well. Maybe it... Oh, okay, thank you. I don't know how that happened. I'll just carry on. TB is valid. So these are technical terms that I'm just defining. Okay, I'll use them later. And there'll be corresponding modalities, T, TF, and TB, that identify these truth values. So TX is true when X is true, TFX is true when X is true or false, and TBX is true when X is valid. Okay? Note that these modalities never return B, so they always return a definite result. And then I'll write that phi is valid at a will W when phi evaluates to T or B. In other words, when the truth value of phi is valid at W. Right? May I carry on? Okay, thank you for loading these two slides into your brain. Let's go back to toy and remember how it works. A participant proposes. If a participant hears a propose, it accepts. And if having broadcaster propose, it receives an accept message, that participant decides. Let's make this thing declarative. We'll do it 3 times. Relative to failure assumptions as follows. Either all participants are honest and live, or all participants are honest and there's a quorum of live participants, but there may be a co-quorum, that is a set's complement of a quorum, who have crashed. And finally, there may be a quorum of live honest participants and the rest may be Byzantine. Here goes, honest and live. Everybody's online. Nobody's messing around. So any rule ending in a question mark is a backwards rule. So let's look at simp except. Supposing that a participant, oh yeah, these are axioms. So there's no W in tails here, no W turnstile thing, because an axiom is something that's supposed to be true everywhere, right? A model is a model of an axiom precisely when that axiom is valid. So this is something that should hold if we've got a correct run of toy. Supposing a participant has accepted. Well, let's look at toy. How can a participant accept? I wonder. What must have happened? Michael, what must have happened if a participant has accepted? Michael said a message must have been proposed. So here we have it. Accept implies somewhere propose. You see? The status of this implication is that if the left-hand side is true, then the right-hand side is true. Let's look at simp decide. If decide is true, well, you may recall, it's here in the protocol, it must have proposed and it must have received an accept message, so we have literally propose and diamond accept. I see people nodding. Anyone have any questions on this? Can I carry on? Hands up if I can carry on. Outstanding, thank you. So that's the 2 backwards rules. The forward rules are just the reverse, right? If somebody proposes, then because everyone is honest and live, wherever we're at, we'll accept. And similarly, if someone proposes and somebody somewhere accepts, then they decide. That's it. Yes?
So in the simp decide, the wherever we're at, you said, is implicit. So the decide and propose have to be in the same location. right?
This is all happening at an arbitrary world, which is a participant.
And how
So-
can you specify, like, decide and propose need to happen at the same location, but not my location? Is that something that you can express?
It is, well, okay, hang on. So first of all, let's talk about the axiom as written. Any atomic proposition without a diamond or a box in front of it is happening here, wherever here is. So in this case, the propose is happening here, and the decide is happening here. The diamond accept is also happening here, but the diamond is true here when accept is true somewhere. So this has the effect of jumping non-deterministically to anyone who's accepted, finding someone. So this, as written, just by construction, propose and decide happen in the same place, which is here. And I think your question was, could I write a different axiom that puts propose and decide in a different place but still the same place?
Yes, exactly.
So in principle, yes, but I'm just going to be a bit disciplined about time. I'm not going to do that right now, but it could be done.
Okay, thank you.
Thank you. Yes.
So strictly now for this theory one where everyone is honest and live, I guess the forward rules actually, if somewhere proposed, then box accepts and box decides?
Absolutely. So what you're pointing out is that, in fact, you've created a lemma. Right? Well done. Thank you for the lemma. The lemma is diamond propose implies box accept. And the proof is simply to check, assume diamond propose, and then apply simp accept bang at every participant. And because every participant is honest and live, they will all accept, and then you have a box accept. So congratulations, your first lemma. Well, first lemma, the first lemma in this talk. I'm sure you've proven millions of them before. Yes. Okay, great. Terence. Microphone, please. Microphone to Terence, please.
Oh, sorry. Would I be understanding correctly if I tried to phrase what you said about the quantification by saying that these are axiom schema, which are there's a space-time variable in each of these?
No, these are not axiom schema. These are modal axioms. Modal axioms hold everywhere. That's the job of an axiom. I actually write it down here, I think, somewhere. Well, it's here. So with an axiom, if I give you a model, you can ask, is an axiom valid in that model? Which means that it has to be valid everywhere. An axiom scheme is an infinite collection of axioms that are syntactically different. This is not a scheme, this is a single axiom, but it's just a predicate. We call it an axiom because we intend that it should hold everywhere.
Okay. So accept itself.
Accept is a, if I may interrupt, I think I know where you're going with this.
Yeah, please.
There's something which I elided from this slide and you have detected, which is a notion of what is actually true or false at a particular world for propose, accept, and decide. So a model is actually a set of participants and a valuation telling us the truth values of the atomic propositions. And this model is a model of this theory precisely when all of these axioms are valid on that model.
Okay. So I get, in a sense, by defining these axioms about predicates, we're defining predicates on models, right? The models which satisfy these.
Yes,
axioms.
exactly. So these axioms determine a class of models, and what you've detected is a hidden parameter, which is the valuation, which tells us the actual truth values of propose and accept and decide on actual participants.
Okay, thank you.
My pleasure. Excellent question. May I carry on? Okay. Let's do this again. Oh, golly, I forgot. Sorry. And correct. Correct just says that the valuation should assign T or F, true or false, everywhere to propose, accept, and decide. And that's because everyone is honest and live. There are no Byzantine truth values here because there's no crashes, no undecided, right? So in a sense, this is speaking to the point you raised, that in order to decide whether this is true everywhere, we need to know what truth values are assigned to propose, accept, and decide, and that is a hidden parameter in the model. I will move on. Quorum of live participants. Hands up who's heard of a failure set out of interest. Yeah, okay, fine. So now, the backwards rules are exactly the same. If accept is true here, then somebody must have proposed. So propose must be true somewhere. But now let's go to here and suppose that somewhere propose is true. Oh yes, and this arrow here means if the left-hand side is true, then the right-hand side is valid. In other words, true or crashed. TB. Different implication symbol. Can you make that out on the screen? Oh, okay. So look, over here, there's a single-headed arrow. Just take my word for it. The forward rules have a single-headed arrow. The backward rules have a double-headed arrow. The double-headed arrow says if the left is true, then the right is true. The single-headed arrow says if the left is true, then the right is T or B, which is valid, which means true or crashed. In the literature, this is usually written as for a correct participant, for a live participant, and then blah-de-blah. That's what this single-headed arrow is doing. And I'll just plug this material. You can get a lot of detailed information into these arrows, and it's really precise, right? I've literally spent half an hour trying to decide how many heads should this arrow have. But that's a feature, that's not a bug, because it's forcing me to think about what I really mean, right? So, supposing propose is true somewhere, then either we accept or we're crashed. That's why we have the single-headed arrow. Similarly for decide, single-headed arrow. And now the correct rule gets quite funky. This box circle means there exists a quorum of participants. I'm just defining it. I'm saying it here. There is a quorum of participants. Supposing there's a quorum of participants for which P is valid, so that's either T or crashed. Then, somewhere, there must be a participant, a P that's true, an uncrashed participant. So this is saying that every quorum contains an uncrashed participant. Hands up who wants me to explain that again. Yeah, sure. So box circle means a quorum. And TB means valid. And P is just one of these atomic propositions. So this is saying there's a quorum of participants who haven't returned false. They've either crashed or they've returned true. And this correct axiom says that if we know this, then at least one of them must be uncrashed, must be true, which actually means, I didn't mean a quorum, I apologize. That's what's called a blocking set of live participants. That's a typo on my part. But just think of this as a failure assumption that any quorum of participants must contain one live member. That's what correct is saying. Yeah? May I move on? Quorum of honest participants. Very similar to the case of live, except that now we have a single-headed arrow here. And the reason is, supposing we accept, that's because somebody somewhere did a propose message. But maybe they're Byzantine. Maybe they sent me a propose message, but not somebody else. If they're Byzantine, then the truth value of propose, because these things aren't messages, they're predicates. For Byzantine participants, the truth values are B. So we no longer know that diamond propose is true, we know that it's at least B. Somebody somewhere said something, they might have been Byzantine. What we know doesn't happen is that everybody has said false to propose. Okay? Any questions? Yes.
Do you mind going back to the last?
Of course. The previous slide, yes?
I'll think about it. Thanks.
You sure you don't have a question? Go on, grab the mic and say what's on your mind.
I must figure that out first.
Fair
What
enough.
is on there?
Would it help if I'm not sure I can zoom in on this. Julia.
I'm also not sure if I have a question, but I have half-baked question. So the first theory when this is second in my brain. So this one is like when everything is good.
Yes.
And the last one where the participants are honest, we kind of assume everyone else being dishonest, possibly. So we add Byzantine to what everyone else does.
So it's not, you're nearly right. So these are axioms, so they're restrictions. So it could be that everyone is honest and live in this situation. It's not that the Byzantine participants have to return B. It's a restriction that at most a certain number of them can return B.
Yeah, so I mean, if they might be Byzantine, we kind of can consider the worst case scenario when everyone does the worst thing they can.
So this is a canonical worst model, absolutely, yes.
And the second, I'm not sure what statement I can make about this one.
The same, except that instead of being Byzantine, they're crashed.
I see. So
but the difference
when
between
they can crash, they crash basically.
Yes, that's right. So the difference, where I really like this because it makes it clear, to me at least, what the difference is between being crashed and being Byzantine. With Byzantine participants, the backwards rules as well as the forward rules are weakened because people can lie. Whereas with crashed participants, the backwards rules work just fine, and the forwards rules are weakened because people can crash.
So just last summary, right? So the first theory, nobody crashes, nobody does something bad. It's like ideal world. Second one, someone might crash. Third one, someone might do something bad.
Yes.
Okay.
Thank you. Christopher.
This might be just a question of notation, but as I read simp accept in theory 3, given the definition of single-headed arrow, it says that accept implies that somewhere propose is true or B. But what you said in your oral description, as far as I remember, was that accept implies that somewhere propose is true or B.
No. On the left, so the single-headed arrow is if the left-hand side is true, then the right-hand side is TB, true or B.
Yes, sorry, it's a simp accept question mark. My
sorry.
question is the precedence between the arrow and diamond. As in, is it the case?
I almost certainly misspoke. So if diamond finds someone who is B, it'll return. Diamond tries to be as true as possible. So if diamond can find someone who if it can find a T, it'll return T. If all it can do is find a B, then it'll return that B.
I see.
Yeah. Thank you for checking that. Terence has a question.
Can you tell me if I'm understanding your intent here? At first, when I saw you were
I can't hear your question either.
Oh, sorry. Thank you. Can you tell me if I'm understanding your intent here? At first, when I saw you were going to present 3 theories, I thought it was just going to be because each one would get more complicated, so one would prepare you. But now it looks more to me like what you're going to do is actually show how this axiomatic formulation allows us to see where the firewalls are, right? Like, for example, when we see how the arrow changes, one might ask, so is it that we're never going to accept a Byzantine node's proposed? And we can see very clearly, no, that's not where the firewall is. We might accept a Byzantine node's proposed, for example.
That's right. So this isn't a question of complexity. These are 3 fundamentally different theories. What I'm exhibiting is how the failure assumptions get worked into the arrows, basically. And what, again, I'll plug this material. Thank you. What's nice about this is once we've written down this theory, we don't have to think about failure assumptions anymore, except to check sensibleness. Now we just have a logical theory and we can push symbols around. Okay. Right, so one more bit of background and then we'll be on to Bracha broadcast. I just tell you a bit about semi-topologies. A semi-topology is a set of participants and some open sets on those participants. Open sets correspond to quorums, which you may have heard of. Closed sets correspond to the complements of quorums, which I may call co-quorums. And then there's a thing called a blocking set in the literature, which I may call a contra-quorum, or, using topological terminology, a dense set. A set is dense when it intersects every non-empty open set, straight out of the topology textbooks. This is exactly the concept of blocking set from the literature. And failure sets, they're called failure sets in the literature, they correspond in effect to closed sets. So if you actually look, for example, as a typical situation, we assume there are 3f plus 1 participants, and a set is open when it has size 2f plus 1, and blah-de-blah-de-blah, all of this stuff. It's topology. I don't mean it's like topology. These are topological notions, right? Every time you see in the literature someone says, assume a set has size at most f, they mean it's a closed set. Right, that's exactly what they're saying. And when they say, suppose D has size at least f, they mean it's a dense set. Right. Okay, I'll move on. Oh, Anthony.
If it's just topology, why do you call it a semi-topology?
Because it's not a topology.
Thank you.
Okay, so difference between semi-topology and topology. In topology, the intersection of two open sets is open, necessarily. In semi-topology, it's not necessarily open. So a semi-topology is a generalization of topology where we remove that restriction. And it turns out, and there are references in the slides to this, it turns out that semi-topologies actually have very different behavior from topology. They're not just quite like weak topologies, very far from it. And semi-topology, the point I'm making here is much of the literature on consensus is actually semi-topological. It just doesn't say so. Yeah, does that answer your question?
Yes.
Yeah. And the other thing I just wanted to say was, even though semi-topologies have their own character, most of the concepts of topology carry through, like open and closed and dense and continuous function, and they have meaning for consensus. So there are things that happen in consensus algorithms that can be phrased topologically in terms of dense sets and continuous functions, and it makes perfect sense. Right? They've rediscovered topology, except it's not topology. Right. Okay, shall we do hands up who wants to do Bracha broadcast? Okay. So a designated sender, participant broadcasts V. Do you have one of those tablet chunks, Patrick? Are they still there? Yeah. May I have one of them, please? Thank you. I just need a sugar jolt.
Also, your son Ruben is watching.
Thank you. Hello. I'm going to enjoy this tablet here. There's one left. Would you like it? What a pity. It's in Switzerland. Okay. Oh. Yes.
Your wife asked to wave. There you go.
Thank you for that. Okay, so Bracha broadcast. Somebody broadcasts a value V, and we assume that all messages arrive. If a participant receives a broadcast, it echoes V. All participants echo at most once. You know what? It doesn't matter if you follow this, because I'm going to axiomatize it in a minute, and that's a far better way of doing things. Sorry, did I say that out loud? If a participant receives a quorum of echo messages, or a contra-quorum of ready messages, then it declares itself ready. And if a process receives a quorum of ready messages, then it delivers. whatever. Even reading this, I have to say, and I've studied Bracha broadcast, I can't hold this all in my head at once for myself. Maybe I'm just a bit tired at this point, but it just doesn't sink in. Here's the axiom system. I'm not sure I want to go through every axiom unless you want me to. But let's just go through a sample. Let's look at this one here. Supposing that here and now, well, here we deliver V. So how can that have happened? Well, it must be that, yeah, here we are. There was a quorum of ready messages for that value. But I've used the single-headed arrow because there might be Byzantine participants who've been sending lying, cheating messages. So in this logical model, they're delivering B. So we don't know that box circle ready V is true, but we do know that it has truth value B. Julia.
So the box with the circle is quorum or blocking set? Because last time I think it was blocking set, so is it the same or different or?
Sorry, I wasn't clear. So box circle literally means there is, find me a quorum.
So it is a quorum?
Yeah, there is a quorum of ready Vs, that's all it means.
I was just referring to a previous slide when you said like something about quorum, but it turned out to be blocking set, I think. So
It turned out, oh, blocking.
Yeah.
No, that was, either I was imprecise or there was a misunderstanding. The definition of this symbol, I misspoke earlier. I'd put a subject heading that was wrong, but it doesn't matter for this. I now define box circle to mean there is a quorum, and that's it. Thank you. Any other questions? Okay, I'll carry on. So the backwards rules, I mean, if you just read this, they turn into that. It just does. Forwards rules. Supposing there is a quorum of participants, I'm just going to, I want something simpler. Let's go to this one, it's simpler, this one here. Supposing there is a contra quorum, a dense set, a blocking set of ready Vs, then we will do ready V. Yeah? Unless we're Byzantine, in which case we might return B. And that corresponds to this, yeah, or a contra quorum of ready messages for a value V. So, in the interest of time, with your permission, I'll just slide over this a little bit, but the point I wish to transmit is simply that this formalizes that. Okay? Hands up if you're okay with me moving on from that. Yeah, okay, thank you. Yes, Michael.
There are two exclamation marks on the BR ready. Is it?
It's just a name, but there's something very interesting. This is a really interesting aspect of Bracha broadcast. Bracha broadcast has this forwards rule. If you have a quorum of echoes, then you declare ready, and that's here, the first half of line 3, of point 3. But then there's this interesting or a contra quorum, and that's BR ready double exclamation mark. So there are, because there are two ways to be ready, there are two forwards rules. That's all. I could have called them BR ready 1 and BR ready 2. But I didn't for a specific reason. There's a BR ready question mark here that goes to a quorum of echoes. So in some sense, this is the forward rule corresponding to that. And this is something else. It's a forward rule, but it's extra. That's why I gave it double exclamation mark. It has a different status. And there's no backwards rule corresponding to BR ready double exclamation mark. There's no rule here that says ready V arrow diamond circle contra quorum ready V up here. And that's a serious design decision why I chose to reverse the first half of point 3 but not the second. If you think about it for a while, it's just because if one participant is ready, because some other participants were ready, then one of them will have found a quorum of echoes, or if not, then one of them will have found a quorum of echoes, and so on. So there's no need to have the forward rule. But that didn't come for free, right? Somebody had to sit and think about that when they were designing this axiom system, right? So this raises the question of which is right. Is this truly Bracha broadcast, or is this Bracha broadcast? Because if you just translated this mindlessly, there'd be another rule here. And the question is that rule a rule or a lemma? And by omitting it, I chose to declare it a lemma. That's a design decision. Entirely defensible because it's derivable from the other rules. Right, so the axioms are really forced me to think about what this actually means in a ways I would not have been able to do otherwise. Right, okay.
So I do have a question. So
Please.
The first thing is about the notation, about this. So in the BR deliver, you have this existential. Is that a
Yes.
typo, or what is the meaning
No,
of that?
it's not a typo, and it's what I was hoping to elide in the interest of time. Let's look at. Let's look
Okay,
at
sorry, but so what I'm trying to understand is if I want to use this declarative approach, right? I do need to give sense and understand the motivation of having these forward rules and backward rules, because if we look into the previous examples of the theories, it seems like there is some kind of redundancy as I understand the interpretation of the arrows, right? So, for example, if we go to the theories, number 1 and 2, I think in the number 1, yeah, there is a clear distinction between the arrows, between the backward rules and the forward rules, right?
what distinction they use the same.
Sorry,
double-headed
like
arrow.
no, sorry, there is no distinction. That's the point. So, you want to mark that you can have these forward rules and backward rules. Maybe the logic can just use a different connective, like a by implication, and not have these. You
Right,
understand
so
where I'm
I
getting
absolutely. So Jonathan is saying, can we? I'll answer that.
Okay.
So Jonathan has suggested just use a by implication.
But in the second theory, it doesn't work because you have a different interpretation of that, right?
Yeah, in theory 2, there's an asymmetry. But we could have an arrow that's double-headed on the right and single-headed on the left.
Yes. So what I'm feeling is that there is some kind of redundancy in presenting your axiom system, but I want to understand why you actually, this is a design choice, right? That.
Let me answer you.
Yeah, okay.
Early versions of these axiomatizations just used an if and only if. And then I realized if and only if wasn't right for this kind of situation. So I actually had, I kid you not, Isaac may have seen these things, double-headed going one way and single-headed going the other. Right? I did that. It's not the right thing to do. These are two separate, backwards and forwards are distinct entities, and I will prove it to you in 2 ways. Supposing BR echo exclamation mark was broadcast V implies echo V, which it would just be the reverse of BR echo, BR ready, yeah, BR echo question mark. So we just take this thing and we flip it round with a V. That would be wrong because a Byzantine participant could broadcast 2 Vs. And according to this axiom, an honest participant would have to echo both of them. But the rules of Bracha broadcast say that you have to echo the first one you get and then ignore the second, right? It's in here. Each participant will echo at most once. So if we just took BR echo question mark, and I went through this, right? I made this error. If we just take this and put a slap a by implication on it, it's not just redundant, it's wrong.
Right.
Okay, fine. So then what do we really mean by the forwards rule? I put it to you, and this is not obvious, that the forwards rule should be if there exists a broadcast. If there exists a V such at broadcast V, then there exists a V such at echo V, not necessarily the same V.
Yeah, okay.
Okay. How about all the other rules? Why are they all existentially quantified? Because in fact, the other rules don't need this kind of choice. Bracha broadcast just has this choice once, And I just want to point out that in the source material, this choice is made canonically. It's assumed that messages are ordered and you're supposed to choose the least first you get or something. The logic doesn't have any of that. It just has this non-deterministic choice of an existential, right? Because we're being abstract. The other rules don't need that. So why have the exists there? Two reasons. First of all, if I didn't, then there would be redundancy. Because if we have a quorum of readies, then we can conclude that we have some deliver, and then we can use the backwards rule to figure out which one was delivered. So this is actually weaker with the existentials, but there's an even better reason for doing it this way. I'll just say this and I'll stop on this slide. It's really good for catching bugs. Because if I do it this way, then I need to prove as a lemma that box circle ready v, quorum ready v implies deliver v. That now becomes a lemma, not an axiom. And in proving these lemmas, I found countless errors in my own axiomatizations.
Okay.
So built into this is some kind of test suite. The exists, tests. It seems to be good practice to existentially quantify as much as possible in the forwards rules and then prove the more powerful by-implicational version, where it's valid at all, using the backwards rules. This is a really good way of catching errors. Yes?
Thank you.
Thank you. Great question.
I'd like to understand the notation on your first two other rules. So the first one means locally wherever I am, I will always echo a truthy value. So either
it means I echo 0 or 1 values.
Okay.
So it's just notation that I haven't told you. Exist 0 1 means it's affine existence.
And then and the second one means somewhere someone will have broadcasted a true value?
No, it means there's at most one value that anybody broadcasts anywhere.
I see. Thanks.
Wonderful question, thank you. Any more questions? So Christopher is twitching in his seat. You've begun to... So I will move on. Honestly, there's basically... There's a lot more we could... Yes?
But then, sorry, that second rule, I will at most broadcast once? That's
sorry, did I misspeak? This means there is...
Someone who has...
There is one value such that somebody broadcasts it. Now, if 2 participants broadcasted 2 values, then this would be false. This is unique existence. There is a unique value such that somebody broadcasts it. Such that anybody broadcasts it.
Even in a Byzantine context?
Aha! Great question. So, I'll tell you for free.
Thanks.
That exists unique B has truth value B. Sorry, that exists unique V dot B. So we're looking for a value, and then we throw the value away and we just return B. So the Byzantine. The truth value of that predicate is B, not T, but B. So yes, exists one diamond broadcast is valid even in the Byzantine
I
case.
see.
Ah?
Thanks.
My pleasure. Yeah. This is, exists and exists one, exists 0, and really interesting in 3-valued logic. As I was about to say, there's a lot we could talk about, which is all documented in the Paxos paper, by the way. There's truth tables and all sorts of stuff, so it's all written down. I think I can skip over this now. Oh, well, I'll just mention one thing. I was tying myself up in knots on whether to read this axiom as there exists a unique value such that someone broadcasts that value, and there exists a unique value such that anybody broadcasts that value, right? Now, without this axiom, which is precise, it's impossible to know what the author meant. There exists a unique value such that someone or such that anyone. This is actually underspecified. And from what I've seen, in order to disambiguate this, you need to find someone who did a PhD with the guy who wrote the paper, or someone who wrote that paper and ask them, right? So I see this as, previously I let slip that I think this is a better way of doing things. So this substantiates that. It's not just about axioms. This is precise. It has a precise meaning. Whereas English is not precise. It just isn't. So here are some informal correctness properties from the literature. And I copied this. Patrick, yes. Bless you, Isaac.
It's a very stupid question. How can you know the difference, though, between the intent of the author, between the notation and the natural language?
Well, often I couldn't. I did not understand Bracha broadcast on my own. I found myself an expert in consensus and asked them a million questions. And we had like, I've lost track of how many failed axiom systems for Bracha broadcast and Paxos we came up with. Right? I could not have done that without asking someone what they actually intended.
But what if they don't really know what they intended?
Amen. We should be doing this. Right? Yeah. I agree with you. Do you have any other questions? Thank you. Absolutely. So, I'm being a bit melodramatic here, but I'm not sure I understand what this means when you really start digging into it. Right? I copied it out of the literature. It looks like it has meaning, though. If a correct process broadcasts some value v, then every correct process delivers v. You suggested a lemma along those lines, right? So here we are. There it is. If someone broadcasts v, then we deliver v. The single-headed arrow takes care of all of the correctness assumptions embedded in the English. Right? Notice that this has a turnstile next to it. That's because this isn't an axiom, it's a lemma. So if a model satisfies these axioms, then this will be true of the model. Okay. So you can have fun turning these validity, these correctness properties into axioms. And if you try, you'll find there are a lot of design choices and it's not obvious, right? It's so easy to read this stuff and go, yeah, that makes sense. No. Right. This is precise. Okay. I'm going to skip over this, though, and I'm going to talk briefly about three-twine semitopologies. A three-twine semitopology looks like this. Any three non-empty open sets have a non-empty intersection, three-twine. In the literature, this has been called Q3. I'll call it three-twined. You see, Bracha broadcast, these correctness properties, they only hold in a three-twine semitopology. And you won't find that written in the literature. What you'll see people writing is, supposing there are three f plus 1 participants and open set, many of you will have seen these things. What they're actually saying is that the semitopology is three-twined. That's the only thing they actually use. So what does it mean to be three-twined? Well, I showed you a picture. I'll try to show you a picture. There, okay? It means that. But we're working in logic, so the game we play is we want to internalize that as a logical assertion, and there are three ways of doing it. One is to say, if we have three quorums, one has phi, one has psi, and one has chi, then somebody somewhere has all three. Aha! That's a literal translation of the Venn diagram in logic. So you can just write that down as an axiom. Bang, done. But there's smarter things you can do. You can lose the chi. You can say if we have two quorums of phi and psi, then we have a dense set, a contra-quorum, that has phi and psi. And this is slightly less obvious, but look. Supposing our two quorums are A and B, and now we have some other open set C, well, it has to intersect A intersection B at ABC. So that means that the intersection here, AB, is dense. It intersects every other open set. Hmm? Just go back. Yes, Isaac. Right, Isaac has said, how do you define contraquorum? A contraquorum is a dense set. It's a set that intersects any open set. In the literature, I've seen this called a blocking set. Co-quorum. Yeah, absolutely. If you can think of a better name than contraquorum, let me know. But I mean, topology already has the answer. It's a dense set, right?
But it's a contraquorum.
Right, so yes.
Yeah, I was thinking about. I was thinking about if I want to implement this, I can think having a set P, and the open sets are basically byte strings that encodes whether the subset, I mean like a characteristic function, right?
Yes.
So a tree-wind a semi-topology will be basically take these three strings that represent the subsets and make the XOR, I think, and just check that it's not 0, right?
You say...
so that's basically encoding the subsets as byte strings, right?
Okay.
And then you want to characterize the semi-topology tree-wind, right?
You want to characterize the semi-topology?
Yeah,
oh, three-twine. Three-twine,
sorry,
yes.
And the contraquorums, for example, is just the negation of the bit string that represent the...
No, that's a co-quorum.
Yeah, that was my question.
So a co-quorum is a... I'm a little uncomfortable here just because topology already has words for these things. So the notion in distributed systems of quorum corresponds to open set. And once you've fixed that, complements of open sets are closed, and sets that intersect all opens are dense. And that's a standard terminology that's been around for at least 150 years, more. I don't know when topology was invented. But in distributed systems, there's a notion of quorum. So the complement of a quorum would just be called a co-quorum. That's just standard sets terminology. And I invented this word contraquorum for that thing that really is just trying to say dense. So it's a parallel terminology that just starts from the word quorum.
Okay.
But all it's doing is repeating the topological notions.
Yeah. Yeah, it's just, I remember that there is, in type theory, there is, by Martin Escardo, introduced something that is called topology types. Well, basically you can encode things using Boolean functions, right? Because you have this correspondence between subsets and byte strings.
Yes.
And anyway.
Sure, so if you want to calculate the complement, that will give you a co-quorum, God help me, or a closed set, yes. I'll just mischievously note that the natural target for semi-topologies is maybe 3-valued logic, not 2-valued logic. But I mean, for implementation, we don't care. But I will move on if I may. Yeah? Okay, thank you. Yeah, so the final thing, and I think this might be my favorite. This only has one predicate in it. If we have a quorum on which phi is true or false, and another quorum on which phi is true or b, then we have a dense set on which phi is true. You stare at it for a little while, it'll become, quote, obvious. But what I like about this is it only mentions one phi. So the notion of being three-twined is now characterized using just one predicate symbol. And in fact, in practice, in the proofs, this is the one we tend to use, because TF means correct. So we're saying if something is correct on a quorum, which is a standard failure assumption, we have a quorum of live or, honest participants, and if we have a quorum of valid participants, so they return a T or they're hostile, then we have a dense set of honest participants, right? return true. This is actually, again, you can see the trace of this in the proofs in the literature. This is what tends to be used. Okay, I'll move on. I'm over time. So I could show you the axioms if there's time. There isn't, but that's fine. Anthony, yes.
So one thing that's sort of been going through my mind through this talk is that when you read about distributed algorithms, there are lots of theorems that say something like, assume 2/3 of the participants are live, and then you can conclude blah, blah, blah. Here you've taken this sort of quantitative description and turned it into a purely logical one. Is it your opinion that you can take those, essentially all the quantitative assertion about distributive algorithms and turn them into some purely logical version?
All the ones that I've seen, yes.
Okay.
The two big ones are two-twined, intertwined, meaning the signature of that in the literature is 2f plus 1, and the failure assumption is f plus 1 honest or live participants. And the other one is 3f plus 1. And say again?
I can find you a 420 and a 520
Now,
algorithm.
yes, so I'd like to be collecting these things. In the IC3 conference, somebody presented something that looked like it should be 5-twined, and I questioned him about this as we were walking along a frozen lake, and he said it's not quite 5-twined. It was something really weird, and I emailed him a couple of times to find out precisely what it was. So there's other stuff out there, and I'm itching to logically represent whatever that thing is. Certainly the two big ones, 2-twined and 3-twined, are absolutely straightforward, and I've just treated the 3-twined case. The 2-twined case is even simpler. Does that answer your question, Anthony?
Yes.
Yes. Thank you. Thank you. Okay. Any more questions? Okay. Okay. So, conclusions. Thank you all for coming and for listening. It is possible to treat decentralized algorithms as axiom systems. We can do this in a modal logic over a semi-topology. And you've seen the semi-topologies manage the quorums, the modalities manage finding quorums, they manage Byzantine participants. You've got a whole bunch of different arrows to define fine details of failure assumptions. Difficult reasoning gets reduced to, or at least formalized as, formal logical reasoning, which I personally find so much easier to deal with. Right? This is a powerful technique. It's not new, right? Axiomatic reasoning goes back to Euclid, but it hasn't been done for consensus algorithms in this particular way. That's the innovation here. And it works. It works for me personally, understanding these algorithms, and it has also helped to catch real bugs. And if you're interested, here are the sources for this talk. Thank you very much.
All right. Thank you, Jamie, for that lovely and very invigorating talk. Are there any further questions from the live audience?
Thanks, that was a really good talk. Could you go back to your last slide before this? Yeah, so your point about that it's helped you find bugs in Bracha?
Not in Bracha.
In Paxos, or
in heterogeneous Paxos.
In heterogeneous Paxos, yeah. Would you say it's a useful tool also for working on new consensus models? So
absolutely.
Okay.
Well, heterogeneous Paxos is a proposed consensus algorithm, and applying these techniques discovered 2 errors in the proposed algorithm.
So to make my question more precise, so in this case it's heterogeneous Paxos is created, and then one uses this tool to understand it and find bugs with it. But for using as a tool for exploring what other consensus systems may be possible. So it's an issue I have with category theory too, where it's good for categorizing existing knowledge, but I find its applicability for creating new knowledge limited.
Yeah, so the proposal is there's two ways to read this, and you're absolutely right. One is, can we specify what properties we want, and then just, let's find an oracle with infinite resources and just ask it, please find me a bunch of axioms that will imply these correctness properties. We could just do a brute force search or a directed brute force search. Absolutely, that is certainly a possibility. That's one answer. Another answer is, what I personally would like to see is distributed algorithms being communicated with this as primitive, obviously with English explanations as well, right? And to some extent, this is already happening. Between myself and Isaac, we are working on consensus algorithms, and what I'm working with is the axioms. I come up with an axiom, and Isaac says, no, that's not what I mean. And I say, well, Isaac, can you write down an axiom that is what you mean? And we're exploring the space using symbols. Now, in the background, Isaac has this amazing, huge engine of counterexamples and deep understanding, which I don't have. But the communication channel is now mostly through axioms. So it's useful for that as well.
Very cool, thanks.
Thank you.
Yeah, maybe this isn't obvious to others, but can you put this in a theorem prover and like define your errors? Yeah.
Absolutely. I mean, I haven't done it yet, but this stuff would be absolutely straightforward. It is just a 3-valued modal logic over a semi-topology. There's nothing mathematically complicated about that.
Thank you. Yeah.
Any questions from the internet? Okay. All right. Thank you all. That was the end of track 2 of Anoma Research Day. So we hope that you were delighted by our distributed systems, or perhaps the Scottish tablets. We will be back at 18:05 CET, which is in about 30 minutes, for the final track covering systems design selections. Don't miss it. See you soon.
Thank you again.
Liftoff. Welcome back to Anoma Research Day. This is Anoma Research Day. If you are not here for Anoma Research Day, you are in the wrong place. Check your URL bar. We are now in our third track of today. The third track, namely Systems Design Selections, will start with a presentation by Jeremy on the System of Anoma. As a friendly reminder, you can always leave questions, comments, requests, etc. in the chats online, on the X stream and the X and YouTube streams, and we will take a look at them and forward those to the presenters. Jeremy, take it away.
Hi, thank you. It's going to be hard to follow up from the wonderful talk that Jamie gave, but I will try my best to do decently. So I want to talk to you guys about the System of Anoma and kind of what it is. But first, I kind of want to get at what does Anoma actually set out to do? I've heard Anoma sets out to be a coordination mechanism for enacting other people's intents. Further, Anoma wishes to have mechanisms to ensure trust between multiple parties, and we don't want to be horribly slow and every participant to care about every other state while doing this. I would argue that the first point kind of leads us to being really a general execution platform, because people's intents, that to me sounds like we're trying to compute some type of computation, and it seems like we have some general idea of computation that we wish to seek out and solve problems with. Further, if you want to ensure trust between multiple parties, it seems like consensus is quite useful here, as this is how we come into an agreement upon certain facts of the matter. And thirdly, something that makes Anoma quite interesting is that we do not want to be horribly slow or every participant to care about every other state of the network. If you look at blockchains like something like Ethereum, everything is on one global computer where you have a bunch of data on there, which I would argue does not scale very well, nor gives you kinds of the properties that you want to see. But how do you even get these properties of having this? Well, I would argue that in order to be useful and to do this properly, we have to be a distributed operating system. And the question then becomes, what is a distributed operating system? This is always the nebulous term that we all struggle with. But all that I mean by this is that it's an operating system in that it provides an environment to operate inside. For example, you most likely have a Windows machine or a Unix machine, but if you're operating inside of a Unix machine or even a Mac, something interesting is that I would argue it is a C machine. You have a compiler for compiling C code, you have documentation via the man pages, and it provides a decent enough environment for computing C functions in which we grow things on top, like higher level languages, GUIs, stuff like that. And lastly, that it's just distributed in some way. I don't really have a formal notion of how it's distributed or which parts, but the operating system just must be distributed in some capacity. And in order to explain it, I kind of want to break this down into a few layers. The way that I kind of want to stack kind of viewing the abstraction process is that at the base layer, there exists some hardware. This could be an existing operating system like Unix. I don't particularly care. Lastly, layered on top of that is some kind of runtime. And the runtime has a lot of interesting things, like I'll get into what engines are, objects, and something called Anoma level. Very bizarre. And then lastly, at the top of this stack, after we have a runtime defined to start evaluating things, we can talk about more high-level things like controllers, which are, I will get to that in a bit, resources, whatever resources are, and local domains. I want to kind of go over each of these layers in kind of greater detail and give meaning to each of these, because currently to me these just look like a bunch of words. The base hardware layer. As I mentioned, this is just the base operating system that we're running things on. We could theoretically run this on an x86 64 chip, just having Anoma being the operating system on top of a normal x86 64 CPU. We can even have custom hardware and have really cool stuff like hardware GC, which would be really fancy and wonderful. But in reality, I think for the time being, we must settle on running this on the operating system of Erlang, also known as the Beam, which sits on top of Windows, Mac, and Unix. And yes, I count Erlang as an operating system because it has system monitors, it has interrupt routines. It is, in all essence, an operating system, and we operate inside of it all the time. It is beautiful, truly beautiful. Before we get to talking about the Anoma runtime, I kind of want to give some motivation as to why the runtime has some of the features that it has. And by doing this, I want to describe the higher level operating system, which is kind of the domains that we're working inside. And the first thing I want to talk about is controllers. I believe often controllers are called blockchains. So I think we can view Ethereum as a controller. And the participants who validate the state are called validators. And it's great, right? You get a bunch of people together, they agree upon certain facts of law based on some programmatic rule set. And a certain amount of participants can be Byzantine, but that's fine. Consensus is great for doing this. However, Anoma is interesting. It's not just one controller. The Anoma network is just not one blockchain. Rather, there's a bunch of controllers. For example, we may have a controller that talks about hotels, and you may have just a single chain for dealing with hotel transactions and another one for dealing with trains. And these can even come together in weird ways known as like chimera chains. And there's even useful stuff even for your own computing. And in fact, I would argue that controllers ought to be programmable and that users ought to have an easy time to program their own controller and rules thereof. I want to motivate this with some proper examples. For example, this is what I want to do on my own computing. I have a bunch of computers. I have my phone, I have a laptop, I have a desktop, and I have a server somewhere in the US. And this is great. I can do computation on my phone. However, my phone is slow. I don't want to calculate prime factorials on my phone. I'd rather ship it off to my computer and then get the answer than just have it on my phone, right? It's horrible that I would have to use a slow device. And so, well, what if you could change consensus such that instead of doing a normal proof of stake or proof of work sort of deal, you have proof of resources, i.e. each of your computers basically says, hey, I have this much computing power and this much storage. And based on this, it gets the weight on, let's say, accepting a job that people submit. And based on this, it will choose the most optimal computer in which to do this operation. So in a way, I would like to be able to change however this controller works to be able to do computation like this. There is other trade-offs too. For example, I believe the default consensus mechanism that we wish to have for Anoma is a very, very fast one. One so fast that we do not want to waste time answering queries which are complicated. Usually this is a service called indexing, and parties could have outdated information or different information or subsets of state. But this requirement, you don't need it for everything. For example, if you have your own computation that only you are sending transactions to, well, this could be as slow as you're sending transactions to. I don't need this to be at lightning speeds. And in fact, it'd be really convenient if I could program and have hooks into different times into this. And so I could slow down the machine, but have different reliability of queries over the system. Some other examples of this is that I think it'd be fairly common to have controllers, not just of yourself, but of you and your friends, right? Like I'd imagine you would have controllers over games that you and your friends are playing, such that you can imagine if you're playing a D&D sort of game, that there's rules that you must abide by, right? Some D&D sets, while some role-playing sets are much more number crunchy than others. What if you don't like the rules in the particular variant that you're playing? It'd be nice if users could push code and have authorization to change the rules while the game is live, because maybe some participants don't like some rule or another. And I think it should be the job of us to design such a model that we can control and change this without people having to hard fork the code base and kind of roll their own thing, because that simply is not practical for non-technical communication and people actually getting real work done. I also want to kind of talk about a local domain. So I was talking before about ways in which participants can agree upon state in a controller, but the problem is that this can't be everything, in the sense that I need something to coordinate these controllers. I need something to say, hey, I want to have a new controller, or I want to be a validator on this controller, or I want to do some complicated things like that. Worse off, you may want to subscribe to various controller states, right? Like, for example, there may be the controller for the D&D game. You may want to subscribe to, oh, hey, is it my turn to start doing things? What is the current state of the game? Can I do anything about it? And I believe this requires long-running processes in some kind of local computational environment. And you really do need something rich to deal with this. Leaving this up to shell scripts is simply not sufficient, right? Because you can imagine that if you do not design this as a proper operating environment, that, oh, okay, maybe it's fine. We have configuration languages like config files for deciding, okay, we have a controller over there and we connect this way, and maybe we have a different language for saying, well, gee, I want to run some logic that everyone agrees upon, and maybe I have some Python code for kind of gluing this all together. Doing this in an ad hoc fashion leads to catastrophes and makes the general user experience not good for anybody. And then there's one component I have not talked about in this kind of operating environment, which are resources and transactions. I would say resources are kind of the core facts that we agree upon, right? We have this thing called the resource machine, and in the resource machine, there are certain invariants that must uphold, and it could even be run in more zero-knowledge environments to hide information to some capacity. And it would be great if we can agree upon rules and we get this via resources and transactions. And what's interesting is that we have a notion of intents. I mentioned at the start of the talk that there is a notion that users can submit intents. Well, what is an intent? Well, I would argue it is just some kind of inequality in this case, right? Let's say if you want to trade 5 tezies for 4 bananas, well, that is an open inequality, right? I'm willing to give up 5 tezies, and I'm just need to look for 4 bananas. And what I find really interesting is that we have seen this kind of in the literature before, in Prolog and quite in particular, in that it can solve for random variables that I throw at it. And I would argue that all solving is doing a unification-like process and maybe doing constraint satisfaction. The exact details don't matter, but I believe that if we could have a declarative representation of computing, I think it would help the problem of solving and dealing with intents quite a bit. And all hail Prolog, we are now making the 6th generation, we're now making our own 6th generation project of Anoma. So I am looking forward to the grand future. Finally, with that all of the way, I can finally start talking about the runtime that kind of holds up this operating system together. The first bit of this runtime is engines. Engines are actors, which means that they can accept messages. They only know about themselves, really, and they can respond to messages by sending more messages to other places. Engines are completely isolated. If one engine over here dies, well, then this engine over here is still fine. They should be completely isolated. It works just like actors in Erlang. The exact details are quite a bit different. But what is interesting is that I mentioned before that in the local domains, we need to subscribe to things. We need to start worrying about, oh, things are coming from this controller over here, and I need to react to it. And this looks a lot like an engine. Like, we use engines as a meta construct for designing Anoma, but I would argue that it is vital that it is also part of the system. After all, we could leverage engines to do the following. For example, imagine you submitted an intent for the 5 tezies for the 4 bananas. How do I know if this is solved? How do I figure out what happens there? Well, if I have myself an engine that is existing on my local domain, I can have it subscribe to the controller for specific things, right? So before I send out the intent, I could have a system event that triggers this to say, hey, please watch out for any transaction that has this resource in it. And from there, I can get information on if my intent failed during the transaction process or get general diagnostic information otherwise. Further, I can even leverage this to send messages to solvers, even written in C++. You can imagine that if I have an engine and I have some way of talking to outside of Anoma, to the outside operating system, either through FFIs or using ports or what have you, I can leverage a live actor to send messages to something else doing work and bring that information into Anoma using processes. So I would argue that engines are very much so a concept in system and something that we should consider for the grand operation of the Anoma operating system. And I think engines are great because actors are really wonderful about dealing with concurrency. I think Joe Armstrong had the right idea. Next, I want to talk about objects. Objects are really simple. Something that amazes me is that if you look at non-object-oriented languages, you have so many concepts. You have modules, you have functions, you have compilers, you have type systems. I would argue all these are objects, and you can derive pretty much everything out of objects. So you can have a very minimal VM and a minimal amount of work to actually realize concepts. So I think objects are just a great abstraction mechanism. For those curious about objects, I would recommend go reading a paper by William Cook about data abstractions revisited. Now, this sounds kind of familiar. They can only receive messages, and objects only know about themselves. This sounds a lot like engines. I would argue to you that objects and engines really aren't too different. I was having a conversation the other day that potentially an engine is just an object with extra features on top. And so I think it is a great basis for dealing with engines. But yes, Jamie, you have to pass him the mic.
Thank you. What extra features or feature, if I have an object and I want to see if it's actually an engine, what should I look for?
The way that I would conceptualize it is if it has a mailbox of some kind. What is interesting is that you can attach a mailbox to an object by composing it in another object. Since objects only know themselves, you can take a mailbox object and the object without the mailbox and have these together work as an engine and have a lifetime.
An engine, I can recognize every engine is an object.
Yes.
Not every object is an engine,
Correct.
and I can tell if something is an engine by checking if it has a mailbox.
Yeah, pretty much. There is a few lifetime constraints and what would actually happen in practice, but yes, basically.
And very briefly, a stupid question: what is a mailbox, please?
A mailbox is just it could be a queue. It's any data structure really that takes in messages that people send for you to process later.
Right.
So rather than getting to the message right away, the object has some computing and it may be stuck processing, and so it can't get to this message quite yet, and so it has to go through the queue in order to be able to respond back to messages.
A queue provided by the OS does not count as a mailbox. It has to be a mailbox connected to the object.
Yes.
Thank you.
Yes, no problem. Something else that is great about objects is that we have over 40 years of research on how to make objects reflective and bend them to whatever we want. And in particular, I would say the meta-object protocol is a great example of being able to take objects and bend them in ways to make them useful in extraordinary circumstances. So you can change how allocation works, you can change how finalization works. It's beautiful. Lastly, I think objects can provide a very clean layer on top of resources. I think something that we've found is that programming in raw resources in the resource machine is quite difficult. There's a lot of invariants that you have to satisfy, and it's not really clear how to do it. It's kind of like writing in assembly, right? You have a bunch of registers. You have to worry about what goes in the register when you're doing basic algorithms. This is all not necessary. And I would argue that if we have a mapping from objects to resources, we can greatly simplify this process, especially since objects are simple in the sense that they can basically model anything. They can model modules, they can model libraries, they can model compilers even, which means that if we can turn the simple abstraction into resources via some mapping, we can effectively turn this local computational model of objects and talking about engines into something that the resource machine can kind of process. And I think this is a great gains for actually making the system quite simple. So I would argue that object orientation is quite great and it fits our use case quite well. Next up, I want to talk about really a language that kind of ties this together. And I dub this language the Anoma level. I would say Anoma level is a declarative/functional object-oriented language. Note that some people will say functional and object-oriented are different because of weird notions, but no. Object orientation and functional are completely compatible and are best friends. You can go ask Guy Steele if they need tail recursion. Lastly, it could be declarative. What do I mean by this? As I mentioned before, when I was talking about resources, it seems a lot like Prolog. And so when I say it's declarative, I believe we can realize a programming model in which we can give it partial arguments and have the missing arguments filled in by unification or constraint satisfaction problem or by having a search, in a way making solving user programmable and giving easy ways for people to write their own solvers and hopefully reason about solving, as it's a core part of the system. Great. So Anoma level will be the language is the interface to the system. I suspect at the end of the day, like many years in the future, that we will have less than 10,000 lines of Elixir and millions of lines of Anoma level to bootstrap all this in. Currently, we have more than 10,000 lines of Elixir, but every day when we develop Anoma, more and more of this Elixir code can be brought in system and we can cut it from the code base. So I am looking forward to having a fully specified, spec'd out system such that we really can have like 5,000 lines of Elixir and have the whole of Anoma. I think what's really interesting about Anoma is that GUIs can be built, right? So for example, we're not all technical users. I would like to program up my system, but I am not everyone. Many people just want to sit down at their computer and have it be useful, right? Like I want to listen to music, or I want to transfer files between my various devices, or I want to browse certain pages that people have made. And I believe that Anoma should aid people in doing these kinds of tasks. And I think that it is, and I think Anoma can aid this both in single user applications along with multi-party applications due to these trust assumptions and sharding. And I believe that the system has a lot of interesting properties. Like for example, we can store all code online. So I can just have libraries out in the ether, and then I can grab that in my system and inspect it. I don't have to go through a weird compilation cycle. I don't have to necessarily get artifacts. I don't even have to go through a build cycle. The code is just already there live. We don't have to go through a build run. All that can go away. Yeah, like everything should be hot code uploadable. Any engine you spawn to subscribe to subscriptions and get messages, this should be able to be upgraded. We should be able to change this because, well, maybe my code was wrong. And you know, we're not all perfect people. We all write bad code. And I would argue that having reflective designs and tools that allows you to reflect in the system can make a system understandable. For example, when my Unix machine segfaults, I have no idea how to fix it. If my web browser freezes, I have no recourse. A normal user wouldn't know how to do anything, but if you know the system and you have the tools, you'd be able to inspect in that, fix that component, or give it to someone who can, right? I could give you the state of the application in its bug state, hand it to an expert, they could maybe fix it, and that would be a wonderful bug report that is actually actionable. Lastly, the language that we design here must be general and ergonomic enough to support all our domains. We must support distributed programming as well as Erlang does, right? We should not be giving a distributed programming language that is worse than Erlang. You know, we need engines and supervisors and all that, and we ought to have declarative programming as this makes it easier to write intents. In conclusion, having complex coordination problems inspires having a proper system to work inside. It is not sufficient to just have shell scripts to make the system come together. That'd be a tragedy. I split Anoma analysis on 3 levels. One is the hardware, then on top of the hardware is some runtime, and then on top of that is the domain where I would say the operating system actually takes place, which is the counterplay between the local domain and the various controllers. Lastly, having a unified language gives us clarity of thought. It makes everything debuggable. And I want to encourage new paradigms of computation by making these systems ergonomic and advanced computer science. I want this to be a system that I want to use myself, most importantly. Yes. That's it.
All right, thank you, Jeremy. Questions from the live audience?
One question from the internet. Do you take any inspiration from Lisp?
Yes. Yes. This is a distributed list machine. It is really a distributed list machine. So, yes.
Michael, or Rob, or whoever.
I have 2 questions. First, we find a bug and want to fix it. How do we roll out the fix in your system?
Sure, there could be quite a lot of different ways. So it depends. So we have a notion of controllers. So if, for example, it is isolated to your local domain, easy. I just recompile the code, hot updates, everything, great. Now this gets tricky, right? If you are the sole validator of a controller, or you control it completely, right? In that case, you can just push out the code by fiat and say, well, I agree to these changes because I control this, therefore it's law. If otherwise, you may have to vote on upgrades. So for example, something I found interesting was that in Tezos, people can provide updates to the blockchain, and people can vote if they like the changes or not. You can have the system as well. I think this very much so depends on the particular controller because users can override the controller mechanism and enact different policies that they want, and even have special privileged users or security patches that they may fast track, which can be security vulnerabilities in their own right, depending on how trust assumptions are done.
Okay, and the second question would be, what's your stance towards client diversity? If everything is written in Elixir or Erlang and there's a bug in Erlang or Elixir, how do we deal with it?
Yeah, that's a good question. My hope is to have at most 10,000 lines of Elixir. I want to like cut this and then eventually maybe have just like a C compiler or something really, really, really fast. The point is that there should be many. The thing that will be, I guess what I encourage is different compilers for the Anoma operating system. And I believe that you can bootstrap this in probably less than 10,000 lines of C, meaning that I think people just make their own. It shouldn't be that difficult, ideally.
Yes.
Yes. JJ asks, how would the resource machine be realized in the Anoma system or runtime?
Sure, in the Anoma runtime. So the way that I would kind of think about it is I'm kind of thinking about it on, let me go up a bit. I'm thinking it around like the domains currently. So to me, I'm still not fully sure, but what I do know is that at the Anoma runtime level, we have a bunch of objects, and there exists a mapping between objects and resources to be able to run in a resource machine. Locally, you don't really need to run the full resource machine because really you're just doing computation in private. You don't need to agree upon it with everyone else, right? It must abide by the rules. You know, if you have constraints on how big a number is, well, that should still be obliged. And if you were to try to submit it online and forge it, well, that's going to fail, obviously. So I think you'd have a resource machine in sort of the Anoma runtime as well to run things against. I think it would be realized in system, and even stuff in the domains, I would argue, is still a part of the runtime. I just kind of split it into these levels as it gives you a kind of different level view of the system, when in reality all the domains are all Anoma level code, and it defines the rest, so the lines get a bit fuzzy because it's a reflective system in a lot of ways.
Rob.
Yeah, my question is related to Michael's second question about client diversity. Where does Beam sit in terms of determinism across different architectures, microarchitectures? Because you mentioned before, like x86 64 is like being like an intended, but I know, for instance, for like WASM, like non-determinism is an issue, like for like Arch 64 against x86 64.
That is a good question, and I do not know. I've not looked into the specifics of Beam on non-determinism on there. I know that if you run the code on various operating systems, you get the same result, but I just don't know about the non-determinism part.
Okay.
Yeah.
The good news, at least compared to something like perhaps threading in WebAssembly, is that the concurrency assumptions or ordering assumptions are very explicit in the actor model. So as long as Beam on different platforms is correctly implementing those, the only thing we would really need to check for is like, are the floating point types not floating point, are the base types implemented correctly and consistently and deterministically, which seems less likely to be a problem. Cool. Other live audience questions? Jan, and then JB.
So, can you write Anoma apps in Anoma level?
Yes.
Is this the expected language?
Yes.
So what's the relation with Juvix?
Well, currently I don't have a Anoma level compiler, and I don't have a Anoma level compiler to, let's say, Cairo or RISC-0 or anything like that. But I guess it depends. Like, for example, you could imagine, just like Unix, there's a lot of languages which compile on top of Unix. For example, I have the Lisp programming language, I have the Erlang programming language. All these kind of compile down to the base platform. So it becomes a question of, is there a compiler down to the level of Anoma level? And like, for example, even without Anoma level, there's a lot of ways that Anoma can be leveraged. For example, I think we have some plans with Juvix to compile out its modules and upload them online, so of having these. So I would say Juvix would be something like a different front-end language in that kind of sense.
At least in part, I understand the idea of Anoma level as a potential replacement in the future to Anokma from the perspective of Juvix.
So, as I understand, you want to kind of create object-oriented abstraction over a resource machine, more or less.
Yeah.
And that kind of implies in my mind that a lot of resources being created and consumed just because you do it unified way. And since we have kind of limitation on the amount of resources in transactions / block / whatever, could it be like super inefficient in the result?
Potentially. I think these are optimization questions that you could align with batch compilation. For example, if you know the inputs and outputs into something, so let's say you have a big chain of computation, but the input to the entry point is 2 arguments, and the output entry is maybe 3 arguments. You can maybe align some of the operations in the middle and optimize it so it's not creating so many objects in an actual transaction that you send to a controller. To me, this is an optimization question that should be investigated more fully in terms of, well, can we provide traces of some of these of these computations, or what can we really do there? So I would say it depends, and I think it's the optimization question.
Thanks.
Jamie.
Thank you for the lovely talk. I read the paper by Cook on something revisited.
Data abstractions revisited.
Data abstraction. And the message I took from that was that every time I hear you say object-oriented, I should hear extensional.
I think so.
Because you don't look inside. The only thing you know about an object is its method.
Yes,
so
yes.
it's fundamentally an extensional philosophy. And there's this lovely line in your conclusions where you write, having complex coordination problems inspires having a proper system to work inside.
Yes.
So I'm wondering how much of this is your ideas about the perfect programming language or environment, with a concrete application being a test case for, and how much of this is the application itself. And to be clear, that's not a criticism. I just want to understand where the boundaries are in the structure.
Yeah, I would say it's hard to say, right? So for example, if we're making video games, something that a lot of video game studios have to decide is, do we make a game engine, or do we just take Unity that is off the shelf? Right. When you make a game engine, you're making an operating system, I would argue, because you're having an environment in which you compute inside. You have to have code reloading of some kind within there, so developers, when they develop, can get updates to their games and not having to recompile the entire engine. You end up designing all these layers so someone can design a game. In the case for Anoma, it's quite interesting. I did not have all these ideas coming into Anoma. A lot of the ideas that I ended up having are are all inspired from the great research that you wonderful folks have done. Like I wouldn't have thought of, oh, maybe if I do declarative object models, and the object model is very weird because I have to think about how it compiles to resources. This is not coming from it from the perspective of this is an ideal. This is kind of ingesting sort of the research that we have and trying to come to a conclusion on how can you make a system usable and friendly, because if our goal is to solve coordination problems and to have systems that people actually use, I think it requires a proper operating system design if we want to get out of just it being crypto, and crypto is just useful for money, right? I want to have like things that I can play music on and have my computer share data. Currently at the moment, I just have rsync, and if I delete a file, it ends very badly. The alternative is to use something like Dropbox or Microsoft Windows and give them all my data. And I would argue that Anoma can give the power to the people in order to have sovereignty over your own state, over your own data, and share sovereignty with other people for coalitions that you may or may not care about. Does that answer your question?
Yes, it does. If I understand, what you've said is complex coordination problems characterize what the OS should do.
Yes.
Thank you.
Yes, Patrick.
Just 2 comments. One from the internet. Somebody said, deep technical architecture breakdowns create stronger builders. Love seeing this level of system design analysis shared openly. So thank you for that. And the other thing I'd say to anybody listening or anybody in the room that hasn't, Jeremy and I did a podcast recently, and Jeremy breaks down his philosophy on system design and architecture, and I would recommend it. It's podcast is called Deeply Intense. It's episode number 4. You can find it published on our stream.
Yes, it's titled Worse is Better.
All right, any other questions, live or remote? Going once, twice, gone. All right, thank you, Jeremy. We will be back in 5 minutes with the last talk of the day.
Good job. Yeah, thank you.
works. How loud is it? Is it you adjusted, right?
All right. All right, welcome back to Anoma Research Day. This is Anoma Research Day. If you are not here for Anoma Research Day, you are in the wrong place. Check your URL bar. We are on the very last presentation, or the very last major presentation of the very last track of this long but rewarding day. And the presenter of this very last presentation will be Tobias, talking about communicating systems of Anoma engines. Will he use the same definition of the word engine as our previous presenter did? If you don't stay, you won't find out. Tobias, take it away.
This is awesome. First of all, I'm so glad into the chat, and then somebody will relay it. And I'm looking forward to questions anytime, basically. Right. Now, yes, exactly. Why am I here? Have one simple goal. One. Well, first of all, we have to finish on time because then it's dinner. But, well, content-wise, it is that we have to get down to these engines, what they are, and why do we call them engines, right? That's the real question, actually. Why do we call them engines? So that's the hard one that I'm going to go light. So it's basically history that I've affected. But yeah, what are these engines? And now I have to, at this point, adjust my script. As Chris asked, well, you cannot just, in the context of Anoma at large, ask a question and say, what is the definition of so and so? You have always to augment the question with which version number. Is it v0.2? Is it v0.3? Is it v1.0? Right? And that's basically the point. So I will give you one definition of engine at the end of the talk, which covers like one central point of engines that I think we should have, and I also add something new. However, I should give you a little bit of context, like Anoma, what is it? And so on and so forth. So, right, on the slide, you keep seeing this Anoma in the middle, and that's the protocol for coordination between these four agents that you see around. So, and what's inside Anoma is these engines, and the engines essentially make Anoma work. That's the short version of how this should be, on the big picture should be. So we have these engines, and they connect to Anoma through the engines, and the engines do all the complicated communications work in terms of sending messages. What you actually see on the picture is an example of a very old protocol. It's the token run protocol. I didn't memorize the IEEE something something name, but it's very simple. So you have a bunch of participants that you see on the outside. They're connected to these engines, which are called interfaces. And so through the what's happening inside the ring is that the engines just pass a token around, and whenever one of the participants sees the urge to send a payload, they will just grab the token, the engine will send the payload around to the next, to the next, to the next, until it's once around, and once I have received as a sender the same payload, I'm sure it's distributed to everybody and can give back the token circulates, and so on and so forth. That's one protocol. And Anoma is a protocol. So, and we have the very same abstraction. The only thing that we change is that we don't have a hardwired network, but we have a network. And so, what I'm going to do to really explain what engines are is first start with a quick recap of what distributed systems are by the textbook. Right. So, and we are in land of message passing concurrency. Who has heard in this audience here or online? You can put a 1 in the chat if you have seen it online, and a 2 if you haven't. Online, who has seen message passing concurrency? Hands up. Who wants to give a definition of it? Thank you. Yeah, but you just had your hand up. Come on. Okay, not fast enough. Yeah, so it's very simple. So we have a bunch of processes in message passing concurrency then, but these are basically going to be our engines. And they just communicate with each other indirectly through a network. And the network is happily accepting messages from each of the participants, and it looks at the message and magically knows where it's going. So each message has addressing information. The interesting thing and the difficult thing is about the network is like, what assumptions do we make? What do you want to do? And here we had a wonderful talk by Jamie on the behaviors of processes, but we can do exactly the same game probably in terms of message logic concerning the network. The simple assumption typically is that each message sent will eventually arrive at the destination, However, the order need not be preserved. That's message passing concurrency, simply. So far, so clear? Great. So now, the new things that we go beyond something that I will explain later is that we also want this interaction with the user. Roughly something that has been also given in the very refreshing talk of Jeremy, like the user wants to interact with the system in a meaningful way. We just say like, yeah, the user interacts with the system, and we are on the most abstract level. It's a direct interaction between users and engines. So then, also in the talk of Jeremy, we had this fact that this necessity that we want to have new engines spawn, new participants join. And this is spawning an actor model language, right? So that's what we want. So there's two more things. We add time. I'll not talk much about it. It's essentially vector clocks. It's figured out. The one thing that I will touch a little bit more is on the computability of these engines. So we're not doing like the fully expressive actor model where engines can do whatever they want, but we want to have these engines that just computers essentially. Right. And that's Alan Turing, by the way, from Wikipedia, the picture, so I don't infringe on any copyrights. Great. So far, so good. So, right. It's late. It's very late. So we'll go a little bit for storytelling time. So I have this promise, and I will hold it. And this is my promise of my talk. I will explain in the end the main idea of what engines are. So, but the engines are this weird thing that's somehow inspired by this stuff. I've joined Heliax about, I don't know when. Who knows? You maybe. Was before the, lovely Adam. Adam was later. It's about 3 years actually. And I don't tell the whole story. It's going to be too long. But for the engines, it is roughly, it was started by, I think, the specific point in time was like when I started looking at StateWrite, which is written in Rust, which is a language that then was the language we were using, everybody, right? And right now we don't anymore, everybody. So things have changed, right? So there's a long trajectory we're having here. So, and then, well, I'm learning the actor model. I've heard like with Jonathan together. Oh, I forgot to say. Joint work with Jonathan and Anthony, whoever he is. And it's great. So yeah, so we looked at the actor model, and it's not the actor model. It's just a whole zoo. It is just a whole zoo. Well, you can say, well, there's the first thesis, and maybe that's your Bible then, but then there's for sure at least one other person in your neighborhood that has a different opinion of what the actor model is. So it's just not there. So maybe one of the reasons why we call them engines is that, not actor. And the other one is from distributed systems land, and I'm pointing at Isaac, state machine approach. All right, that's the other big one. I quickly mentioned in passing the temporal logic of actions, not only because Jamie has mentioned it, but it is having this very nice word action, that somehow these engines perform actions, and the simple actions like sending messages and state updates, spawning new engines, checking time and stuff, right? And then another thing that I just recently learned about that it exists is so-called even condition action rules that actually come from actor database management systems, something that I have never heard before, but this is a beautiful name because it really says what's going on. So the engine looks for an event to happen, then it checks a condition, a predicate on state, and then based on that, it decides, should I do something or not, and if so, what, by the action. And this is actually pretty close to the definition of engine. So, already comments, nodding people, that's always a good sign. And there's Anthony, hello. Great. Yeah, state machine approach is really the point, and here I am changing gears. In that communicating finite state machines, I have to do this trick. That's just out of curiosity now, like who has heard of those before? Yeah, so who has had a course in automata theory? Yes, more people. Who has used?
They didn't cover CFSMs in that course.
Who has used the tool JF Lab? So just in case you want to know about automata theory, there's two ways. You go now to the different tab and you type JF Lab and you download the tool and play with it, or I can tell you in 3 slides what's going on. 3 slides, right? It's late in the day, long day. We have already, all the brains are already exploding almost, but 3 slides for this. So, slide number 1. Moore machines. It's a classic textbook example of state machines, finite state machines. So what do we have? We have a finite number of states, and the graphical representation is the following. So you make for each state a circle, and you write the name of the state upstairs. Then, besides these states, you have transitions. And the transitions always involves two nodes. And you will have, in the first node, you will have upstairs the state where you are right now. Then you have an arrow that reads what is actually being read, what is the input, the message you receive. And based on that message in your state, you decide to go to the other state. And that's already then done. And once you arrive there, you look, okay, what should I do? Oh, I sent a message to somewhere, the output. And then you can look at the whole collection of states and transitions, and moreover, you designate one state, the state in which the machine is right now. So we have now 3 states: listen, copy, and send. For example, if I'm in listen and I receive a 2, then I will transition to the state copy and output a 2. That is really like that is like in every textbook on topology theory. So what is the next step is, how do we make these machines talk to each other? Oh, right. There's always, so the experts out there will say, but no, that's not true. It's not a Moore machine. You don't have a total transition functions. And yes, you're right. We have just a partial transition function. But that's all right. We can do that. But just for the record. Okay, good. Okay, now we want to make these things communicate with each other. First thing is, like, we have this network there, it's back, and we give names, A and B, for the participants. And each of A and B are one of those Moore machines. So attention, here they come, 2 Moore machines. So it's essentially the same as before, just the input and output labels have changed. For example, if you look upstairs and the listen state, if I receive a 0, I also get the information who has sent the 0 and actually to me. That is a technical convenience that it's there. And the question mark indicates I'm reading, and the explanation mark, the bang, is the sending. So, for example, if it were that we put this token into the network saying that B is just sending, B is done with sending, and now B has put the message that to A, that the token is there for you to grab. So what will happen in this state of the 2 states, so the upper machine, both machines in the state listen, and the token is given back, so to speak, from machine B into the network, and now machine A can take the token by reading the message B is sending 0 to A, and it will transition by B, I read 0 from B, and I transition to the state send, and accordingly I have to then put into the network, I consume the message and I put back into the network as machine A my send. So I send my payload, very boring here, to the network. And if you look at this closely, this is actually the token ring protocol I showed you on the first slide for 2 participants in a certain variation. Great. That was slide 2. Questions, comments? Everything clear? Fantastic. Oh.
Just a technical question here. So B is baked into the appears to be, as illustrated, B appears to be baked into the syntax of A.
Baked into the syntax of what?
Yeah, if I look at the A there, it nominates the B that it's going to speak to. So if I replaced B by C, that would be a different Moore machine.
That would be a different Moore machine, and probably the message would never be delivered because there's no such machine.
Okay.
However, this question will be much better explained if I switch to the next slide. May I switch? Okay, great. So now there's the third thing. The label transition system semantics. I will come way at the back why we need semantics, but and this again is basically the last point of recap. So choreography automata, if you look, is actually where this is taken from, but you can see this over here. This definition is textbook, just adapted to our Anoma machines. So we have our transitions from states to other states if you read a message. So machine AJ is getting a message from machine AI, and the message called M. As a response, I transition to the next state Q prime, and I send a bunch of messages, possibly 0. So if this happens in the context, well, the context is not just the machine itself, but actually a finite set of named machines, as I call them. So we have a bunch of AIs. These are the participant identifiers, and they are mapped to actual machines. And moreover, the network is given, the current state of the network is just a finite set of messages with sender and recipient and a payload, right? And then this transition here, I can lift it up to the system such that if it's the case that this message I sends to AJ to M is actually in the network, that's the first clause, like I pick this message out of the network randomly, essentially, if you will. Then I update the state of the machine AJ according to this update of the partial map, technically. And finally, I update my set of messages, right? So I remove the message from the message set, and I add the new messages as they are sent by machine AJ. And this is useful, this label transition semantics, because you will need it for the same reason that we have actions in TLA plus. These labels on the transitions are then essentially action labels, and you can specify properties of the composed system such that for each A message will be responded eventually by a B message and stuff like this, as it's common in the temporal logic of actions of Lamport. Questions, comments? Too much, right? This is a little bit too much for that. Oh no, Robert is still awake. Fantastic.
Your diagram. So your diagram there in the bottom right that talks about AJ's communication of its state machine with its mailbox.
So
and
exactly,
Q prime, which belongs to.
No, this is just like a machine AJ, which has two states, Q and Q prime.
Yeah.
And it is in state Q. Oh, well, I cannot point. I was just told I have to do this now with the mouse, sorry. So AJ is in the state Q, and it, as per indication of this arrow here, and it will read the message and transition in the state Q prime, and accordingly send messages.
Ah, send, got it. But what do you have the arrow back to Q for then?
To indicate, well, the arrow that comes out of nowhere is the arrow that just indicates the current state. And that is terrible.
That arrow comes out of nowhere. That's not going back
that is
from
like,
Q.
yeah, the arrow should come from downstairs, but then
okay.
the slide would have a, yeah,
that makes sense.
Yeah,
Thanks.
that's an improvement of the slide. Yeah, thank you very much. It just looks weird. It's true. Yeah. Thanks for asking. Cool. Then, yeah, this is like the most technical part of the talk, and then now comes the fun part. So, so this is like textbook choreography automata, and now, actually, I'm presenting now another 3 slides, the paper that we've just pushed yesterday to our fantastic ART reports as organized by Jonathan. You should go out there, ART reports, Anoma, good stuff. And we have this new report, and we do now a couple of things with these machines, because so far we're just finite state, we need more. So, in short, we just want to also spawn these new things. But that's very easy. In this case so far, I just enumerate all possible machines, give them a number, and if machine A wants to spawn the machine with number n, it just outputs an additional label and saying like, well, I as machine A want to spawn the machine with number n, and it should reside and be addressable as machine B. I should make sure that B is free, but that's something that you can read in the paper. Very easy. Slightly more interesting is that, well, so for its finite state machines, and I can easily describe them just by tables. Like if you go to the original paper of Moore, he will just talk about actually these tables. He will not talk about transition functions. It will be just tables of state transitions. So now I have a countable state space. To describe a function from a countable state space to something to a countable state space, it's a little bit more complicated than just giving a table. However, that has been figured out. You don't have to reinvent the wheel. It's done. It's computable functions, and between countable sets, and thanks to Gödel, we have at least one numbering of all these functions that we can use. You remember that I said I need to enumerate all these machines to be able to specify which new machine I want to spawn. That's it, spawn someplace. Great. And yeah. So, ta-da, here's the paper, all the details, including the timed case about which I will not talk here. So I will take 2 minutes here. No, I'll take a short break. So yeah, that's the paper, joint work with Anthony, and it's all written up. That is essentially now the point. We get ready for the actual stuff. I can tell you a little bit more, just to prepare you. So, you remember now that I told you about these computable functions, and they're beautiful because that's what you're going to do with the computer, and they can do a lot of things, but many things you cannot do. But the hardest part is like to actually present these computable functions. So if you have a simple function like +1, it's very easy. But already writing a sorting algorithm in any programming language, if somebody gives me the code of I don't know, a first-year student of university that describes a sorting function, I'm not sure it's really a sorting function. I just read the code and I'm going to find a bug. And then what is this function actually? It's really hard to describe in syntactical terms these functions. Yeah, in theory it's very simple. I just give them a number, because and how do I get the number in the case of a specific programming language? I just essentially look at the number that's encoded by the code if I represent it as a number. So basically, if I'm just at the point where I have to specify these transition functions as just any computable functions, it's very, very difficult, in my opinion. So what do we do? Right, engines. And so basically, as the countable state spaces are like typically structured, I might do something clever. I might find out, well, the state bit is huge, but I can kind of discern a finite number of equivalent states, and I just say, like, for each of these equivalence classes of states, I describe via an action what I want to do. And this is the example. So for example, if I have all the states that are kind of touching green, if they receive an A, then they just move to the right. And in the orange states, it's like if they receive a B, they go down, and if they receive an A, they just go to the next row. And this is an example of what we call a guard. And a guard consists of a predicate that says, like, for a message in the state, whether something should happen, and if something should happen, then it moreover describes what should happen. Right, and the engine definition, unversioned, and just the basic idea, and basically I'm very, seeing Jamie there, this is not a definition, sorry. But it could be a definition, and it's not the definition, but it's maybe the engine definition version 2.1 or something, version 0.21. So we have accountable behavior, that means, and it's very simple, two things. So we have our engines that are extended to the countable behavior as described before. So we have a transition and output functions that are just computable functions as per Turing and maybe enumerated with Gödel numbers. So, but we want a little bit the finite state machines from the 80s, because they're very simple and they actually were used to define what a protocol is. A protocol was defined as a communicating finite state machine. So we want that back. And what do? Yeah, in good cases, we can kind of recover the illusion as if we had just finitely many states, or at least we try to approximate with a finite number of guards that describe the behavior. There's one specific special case. If you just provide one guard, you exactly recover the original definition of a Moore machine. It doesn't make a difference if you have one guard or you just have the Moore machine itself, but you are allowed, so to speak, to be a little more general. And there's a lot of trouble that I'm not talking about like what happens if several guards don't want to go with each other, but this is the very simple idea of engine definition. It's just a machine with countable, computable behavior and finitely many guards. How much time do I have left? Don't worry about the time. Dinner. Who's already hungry? So just to give you a flavor, like that, this is connected actually to the literature that I have alluded to before. So this is a beautiful paper for reasons that you will see when you go there. That here's just one of these rules that actually occurs in larger context. And what I want to, maybe with the mouse even, show here is that it's really this on a certain condition, if and on a certain event, if a condition is true, then I do something. And it's a very nice application. And moreover, it has a presentation in terms of Petri nets, and that's why the paper is awesome, because I love Petri nets. Okay. So if you go to Wikipedia and look up even condition action rules, you will find this word trigger, which is actually the one that we use instead of event, because event again is a little bit overloaded. Last but not least, 2 sentences of temporal logic of actions. There we have actions defined in a fun syntax if you have the right spirit. It is possible to use this, but it's well known to be hard, and that to describe, like, so it forces you that every variable denotes a set, and then you force yourself to somehow give a relation between assignments of sets to variables before in the old state, and then somehow you describe how they update. And if you forget to say that something stays the same, anything can happen. So it's really like the ultimate foot gun for specifying system, but it's executable. However, it has in principle this nice built-in notion of a guard, in that if I pair the action with the enabled action predicate, then I get the corresponding guard in the sense that I have described before. To conclude, I have given you the basics of message passing concurrency and explained to you what a state machine is and how they can communicate with each other. And I have quickly advertised what are the extensions that we want to have to describe our Anoma protocol, in terms of that we need to dynamically create new engines, very much like in the actor model. We want to act clocks, which is a technical necessity more than a difficulty. And the one thing that we actually leave out as future work to be detailed is how we want to interact with the user. Right. Then there was this promise. I explained to you what engines are, and really the simple idea that everybody could and should understand, I hope. Please. Yeah, but I have seen so many good stuff. I mean, I feel like I'm the most stupid person in the room. Like, so many awesome discussions. So I'm sure it's here, but out there, like, if you have questions, like, tell me, like, was this a good explanation of engines? Maybe a thumbs up, or like a question like, what is this anyway? Like, or where should I read up? Like, I'm looking forward to your questions. So the 2 ideas are, like, I extend the behavior of machines to be computable, and I allow for extra structure, or I essentially ask the specification person to give this extra structure in terms of finitely many guards, very much like Killer Plus. Very, very important is, why do we do this? We want to specify Anoma. That's what we do day to day, and we want to describe what the Anoma system, the Anoma specification, the Anoma protocol, great. The Anoma protocol does in terms of these engines, which are not fully declarative, but they have the advantage, similar to DLA Plus, that they're in principle executable, so that at some point in time, it could actually be that we have not only the Anoma specification, which is operational in the term as per the LTS semantics, but we actually can execute this LTS. Maybe not in the most efficient way, but as a reference for any other specification. So that's the idea, and it's just the starting point of a journey, I think, that we are all on here in the room. And please ask questions.
All right, thank you, Tobias. Do we have questions from the live audience? Yes, Artem.
Thanks so much for a wonderful talk. So I remember we talked about at a certain point how this, for example, differs from the classical Erlang model, right? If we talk about trying to think of gen servers, right? Gen servers have handlers, and looking through Armstrong, etc., it turns out that it has guards. It has something that we could kind of talk about like guards, but it doesn't allow for a general predicate, right? Those handlers don't allow. So the engine model allows for those general predicates, right? And they sort of almost save space. So from what I understand, there can be several guards activated for one message. Is that correct?
That is exactly something that is out there. So when I was originally bringing up this idea, I was, and also I can actually cite quote Anthony saying, like, right now we actually do this mostly that at most one guard is active at any time.
At most?
At most one guard is active at any time. Because that's the easy case. Because if, like, then the next step would be And then this is really like up to research, and these are design decisions that need to be made and are important. What do we do? Like, do we want to allow for several guards to be in conflict? In which case, I need a conflict resolution strategy such that a serialization is happening. And that's not a serialization in the terms of Isaac. It's just like I really fix an arbitrary order in which they are to be executed. In something like, yeah.
So wait. So is the point that currently you just ask that every guard should not? So is it that you pass the message through all the guards, or is it you pass them linearly? You have some ordering on the finite amount of guards, and you kind of stop and execute the action of the first one, which is matched. What's the behavior, in other words, if I specify 2 guards, like if I send an integer, which is, of course, both an integer and is even, if I send 2, and I have guards on that message that checks, is the message an integer and is the message a 2? What happens?
You want to answer that?
I mean, we are investigating, like, yeah, there are different strategies to evaluate guards, and we are investigating which is the most convenient, or if the model actually can encompass all the strategies, the possible strategies, right? So this is one thing. And the other thing is that this differs, and maybe I'm mistaken here about Erlang, but we are constrained the space of function, right? Because we are saying computable behavior, and if I'm not mistaken, in Erlang you can have any function, right? The handlers, the message handlers can be any function, right? But we are saying here that we want just total functions, right? Because we want to predict the system how it will react to messages. Like, we don't want, we want, for example, to have the engine behavior to always respond and not getting into a loop, right? We always want terminating functions, total functions. So it's different in that sense. That's another thing that we forget to mention, but it just...
What I would add here, like, sorry to interrupt you, is that we are actually writing up another art report on how we would do this in more concrete terms. So that this very general idea of that we start out like with the idea of a state machine, we have the finitely many guards. And what actually is happened, so to speak, step by step in a more refined model is actually in the process of being written up. And we should probably just keep going our weekly meetings and everything, and just keep working it out so that we have eventually a version that will stabilize.
Yes.
Yeah.
Other questions from the live audience?
Great presentation, Tobias. Thank you. Especially the diagrams. How do engines relate to the resource machine?
They're completely orthogonal, I would say, in that the state is completely arbitrary, except for that it's countable. I mean, unless we need like resources that store real numbers, it's all good.
Jeremy, take the mic, please.
Hi, thank you for your talk. I want to have a follow-up question based on what Artem asked, because it had me thinking, could multiple guard evaluations be viewed as like a choice point where, because as far as I understand, at least in this engine model that you have, you've modeled like all the engines, you've basically modeled the entire system. And so you actually know the entire system state at a particular point. Could you model 2 guards matching as a choice point in which you could always backtrack to if, let's say, computation fails in some way, or maybe you're not satisfied with the result? It was just something that came to my mind when I was hearing the discussion.
So concerning choice points, I rather think about if there's a specific choice to be made. Well, like you said, like there's a general situation of there's 2 guards that potentially like competing activated. I mean, if they're essentially like independent of each other, I can just execute them in parallel and nobody will cry, hopefully. Yeah, maybe it's also the wrong thing, but just in case. Like the interesting cases are like if I have essentially 2 choices. So there's two variations. So first of all, the programmer or the specifier has made a mistake, and we should give an error and a warning, or we want this. If you want this, why don't we just ask the user, what should we do? So the main point that I actually didn't hark upon here is that what we want is that each behavior is deterministic. I mean, it was implicit in my presentation that didn't hark up in. So we want to have that actually, if there's a choice point, you rather ask the environment what to do. It could be also a random number generator or something. But and this is if there's really a choice, then it should be exposed to the user. Or you have a resolution saying, like, if I have two things, then I have something like a precedence, and I resolve it that always in the same way, but I don't make a real choice. Then it's just like a conflict resolution strategy. Does that make sense?
Yeah, roughly.
Great.
Other questions from the live audience? Questions from online? Okay. And thank you again, Tobias. We will have a very short welcome. What did we do today? We looked at a snapshot of research in progress. As you saw, we smashed the black box and showed you the internals of what's going on inside Anoma Research, like it or not. We had 3 tracks: resource machine menagerie, distributed systems delight, system design selections. First, Michael introduced the EVM protocol adapter, talked a lot about practically how do we want to interoperate with Ethereum. He had some amazing diagrams. Some of them were cribbed from Yulia, but they're just as amazing. Following that, Xiang told us about the Cairo resource machine, how that works, what resources and actions are composed of, and how they are manipulated, verified, etc. And Kike and Yulia told us about shielded state synchronization and left the question of whether TEEs are a good idea just about as undetermined as it was beforehand. Following that, the second track, Distributed Systems Delight, started with Isaac talking about store, order, and execute the Anoma node execution system, a presentation filled with many, many US states used as representations of abstract states, which I considered very funny when I first saw Isaac do it in a talk 3 years ago, but now it's kind of lost. Following that, Anthony gave a presentation on how the shard and executor engines are implemented, which was very clear, at least concretely, in terms of data structures. And Jamie, in addition to distributing sugar, talked about a declarative approach to specifying distributed algorithms, and we all learned a little bit about what a contra quorum is, maybe. The last track, Systems Design Selections, featured at the outset Jeremy talking about the System of Anoma, and talking about engines, and then Tobias followed that with a sort of more mathematical perspective on what engines are, how they relate to other parts of the literature, and sort of what they are comprised of and why in the context of Anoma. And this is the closing presentation. If you like this, we'll probably do another one. Topics that might be covered next time, or maybe not, we'll see. Generalized proof of stake, metastability mechanisms, Anoma economics, shielded kudos, private solving, realizing multi-chat, and maybe something about idealized Anoma. So, thank you for joining. Let us know what you think. Send questions or feedback on the stream chats, or also in the Anoma research forums, which are accessible at research.anoma.net. We would love to hear from you, and thank you for joining us today.